Hi, this is David Voss, CCIE 11372, and in this video we will be covering network design fundamentals. Specifically, here's what you're going to learn. You're going to learn about some basic internetwork design fundamentals, and then we're going to dig into design methodologies, focusing in on Cisco's methodology first, and then we'll talk at a high level about some other design methodologies. So here's some basic internetwork design fundamentals. Using a structured design methodology provides many advantages to the engineer and the administrator of a network. Specifically, it ensures that all steps are covered when a process is followed. The point being here that when you create a thought-out design and implementation, that many of the aspects that you're not just doing it ad hoc or as you go, because that's when mistakes are made. But it ensures that you follow through on a process step by step, never moving on to the next process of the design and implementation until you're fully ready to move on to that phase. So it provides a framework for the design process deliverables as well. Each phase usually has a deliverable, and each phase would allow you to hand in or receive a deliverable saying, here's what we found, and now we're ready to proceed to the next phase. It also validates that you know how to meet customer and business requirements. It's not enough just to say, we need to change the network, we need to upgrade the network. Specifically, you're addressing a customer or business need. And you need to make sure that when you're planning upgrades, that you are actually meeting the needs of your customer and or the business. So these methodologies, these methodologies you're going to learn about enable you to answer the question, which is specifically, how do we upgrade our network, or how do we adapt our network to service specific issues we're trying to address? Finally, it allows for consistency in the design and implementation of networks, so that whether it's peer review or whether another engineer pulls up a document at a later date a few months down the road, you're implementing network solutions with consistency. But also, if you have a strong peer review process, which is recommended, that your peers are reviewing the actual network implementation so that best practices for the industry are followed. Now, let's get down to the basics of what internetworking really is. And really, it's the communication between two or more networks. Now, this encompasses every aspect of connecting computers together. So it's not enough to, obviously, you know, as an engineer, it's not enough to say we're just going to connect a device into the network. There are a lot of pieces in between, whether it's hardware, software, programming, quality of service. There's a lot of things that are going to play. And in basic internetwork design fundamental is that you're approaching it from an end-to-end design point of view. Now, internetworks have grown to support vastly disparate end system communication requirements. We're talking about, obviously, voice and video as not just the newcomers anymore, but these are standards that you'll find on networks. So there's contention between voice, data, and video all the time. And our networks need to be able to support all three. Finally, an internetwork requires many different protocols and features so that it can scale and can be managed without constant manual intervention. So you will note that large networks can consist of really three distinct components, and that is the campus network, which is usually locally connected users in a building, then the wide area network, which connects these campuses together, and then finally remote access. Now, obviously, for the CCNP switch exam, we're going to be focusing in on campus networks and the switching platforms. So as we focus in on the local area network, it should be noted that today's local area networks are becoming increasingly congested and overburdened. And this is mainly due to the exponential growth of endpoints, whether it's wireless, whether it's mobile platforms, whether it's telephones, new servers, new systems. IP addresses are in constant demand on any network that is managed nowadays. And there's increased congestion, and the network must handle all of these new devices. But also, these devices are becoming more efficient. They have faster CPUs. There are faster operating systems. They're sending more and more traffic out, more complex traffic out. Many of these applications are really network intensive. Now that we've covered some of the basics, let's look at a specific methodology that you're going to need to know for your CCNP switch exam. And that's Cisco's PPD-IOO methodology, or their model. Now, this is a complete life cycle model. It's not just an implementation model, although implementation is a part of it, but it has 7 distinct phases. There's a prepare phase, plan, design, implement, operate, and optimize. We'll discuss each of those phases in depth, but specifically throughout the video series, we're obviously going to be focusing in on the implement phase. That being said, you need to understand all 7. Let's proceed. The first stage of the PPD-IOO process is the prepare stage. In the prepare phase, a company develops business requirements, strategy, and vision. And it's very important that these are considered and established before going forward. Otherwise, the network design won't meet the very requirements you're trying to fulfill. So if this is not the first time through the prepare phase, then this is really a review of the current business conditions, and they must be matched against what was previously developed. And then to discover if any changes were found. Then look at the technology vision and strategy, and if those should change to meet the new conditions. Now, what's going to come out of this analysis will be used in the later processes of the life cycle. But what will specifically come out of the prepare phase will help an engineer or design architect to develop a very high-level conceptual architecture. So typical deliverables from this phase include a high-level design, customer requirements documents, and or a current state assessment survey and results. In the plan phase, a project plan is really the next thing to be developed. Now, if no current network exists, then the project plan will include a number of individual pieces of information that are absolutely required before the next phase can occur. So this includes the allocation of financial resources, physical hardware, and design and implementation information that will be needed for further phases. Also, the development of a network security plan and the development of a project schedule will be required as well. Now, if there is an existing network in place, then the project plan is developed, but only after an audit of the existing infrastructure to see what issues remain, what issues need to be addressed. The typical deliverables from this phase include site requirement specifications, solutions test plan, a site survey form, or customer requirement document response. In the design phase, the company develops or, if need be, updates a comprehensive network design. Now, the information gathered from the first 2 phases are now really put into play, and they are used to ensure that the design actually meets the business and technical requirements that were first stated when you began the project. Now, if everything has been completed correctly, the design will provide a fully scalable and highly available network, and also ensure that it's secure and that it will meet needed performance metrics. Now, there's one key document, although there could be many documents that come out of the design process. A typical deliverable from this phase would be a low-level design. Now, the implementation phase is where the engineer really rolls his sleeves up. And it's important to note, though, the implementation phase isn't as simple as just putting equipment on the network. Generally, it's good to configure a test lab to simulate the different parts or additions of the network design proposed. Now, doing this, it will allow the implementers the ability to discover any potential problems, and if found, they can be addressed. But once everything's been worked out in a test lab, then a full-scale implementation can begin. Now, it needs to be determined who's in charge of the deployment, who the project manager will be, who will be doing configuration and testing. All these things need to be worked out, and obviously that's done effectively by a project manager. Now, the company must also ensure that any integration tasks with the current network are handled carefully. So obviously we're talking about change procedure control here and making sure that things are scheduled appropriately. And not only that, but reviewed appropriately before being implemented. And once the network has been implemented, a series of tests are normally run to ensure that the operation of the new network is working as expected. So these tests are often run and should be run the day of the maintenance, so that whatever was implemented can then be tested immediately, and if need be, using the fallback plan to back out of the change if necessary. That being said, in the implementation phase, the typical deliverables from this phase include a network ready for use test, a test report, and an implementation log. The next phase is the operation phase, or operate phase. Now, this is considered by far the longest of any of the phases in the life cycle, but this is basically because the solution is now in place and you are taking a look at what you have in place without making any major changes to the network. And during this phase, you're spending the majority of your time and the company funds on managing the network and being actually proactive to address any issues. But also, obviously, we all know that you need to be reactive. There will be issues that may come up from the changes, and you must be ready to deal with those. Any minor moves or changes also would occur during the operation phase. Typical deliverables from this phase include a root cause analysis reports and support contract analysis reports, as well as move, add, and change reports. The optimize phase can happen really at any time after a network is operational, but it typically happens when there has been a minor or major change to that network. During this phase, the current or existing business and technical requirements are compared to those that were once in place to make sure that all the changes are actually doing what they've been proposed that they would do. If any changes are recommended at this phase, then the phases can start again from the beginning to ensure consistency and ongoing good design. So as you can tell, this whole life cycle, this whole Cisco design life cycle is never ending. But it does allow you a structured approach on not only how to research what your business requirements are, but really from A to Z on how to implement new ideas that meet business needs. Obviously, for the CCNP switch exam, you need to focus on the Cisco design methodology, but you should be aware of the others. There are many other design methodologies. Some are higher level, some are lower level. Each have different functions that may benefit you depending on the situation that you're in. These design methodologies, such as ITIL or the ISO methodology, often these can be combined with other methodologies to provide a robust design methodology and solutions for your network. So just be aware that there are other methodologies out there that will help you continue to grow in your knowledge, not just in Cisco, on how Cisco does things, but how things are done in the industry in general. So here's what you've learned. You've learned some basic inter-network design fundamentals, and then we dug into design methodologies, specifically focusing in on the Cisco methodology. And we broke it down piece by piece. You'll need to know each phase of this design life cycle. And then finally, we've given you a heads up that there are other design methodologies out there that you should absolutely know about. Just because you're taking a Cisco exam does not necessarily mean that there are not other excellent methodologies out there to be used for Cisco network design. I hope this was beneficial to you. Thank you very much, and good luck in your studies. A properly designed local area network is a fundamental requirement of any company or any business today. Hierarchical network design involves dividing the network into distinct layers. Each layer provides a specific function that defines its role within the overall network. And by separating the various functions that exist on a network, the network design becomes modular, which makes it much easier to make changes in network design, to upgrade hardware, or to implement new services. Let's talk about each of these layers. First, there's the core layer. The core layer is the backbone of the network. The core layer provides interconnectivity between distribution layer devices. So it's important that the core is highly available and redundant. The core layer also aggregates the traffic from all the distribution layer devices, so it needs to be capable of forwarding large amounts of data very quickly. The distribution layer aggregates the data received from the access layer switches before it is transmitted onto the core layer. The distribution layer has additional functions that you won't find on the core or on the access layer switches. For example, at the distribution layer, you're going to provide routing for the virtual LANs that you've rolled out throughout your access layer switches. Finally, there's the access layer, and the main purpose of the access layer is to connect your endpoints directly onto the network. So it services end devices such as PCs or printers or phones. As you will see here in this model, we have the three distinct layers: the core, distribution, and access. The access layer is providing connectivity for users and work groups, while the distribution layer is applying policies for routing or maybe even quality of service. And then finally, the core layer is simply providing high-speed switching. Now, as you can see in each layer, we have redundancy built in, but on the core layer, it's especially critical. Now, for a medium-sized company, and this will happen frequently, or at a branch office, there's not really a need to build out a separate core and distribution layer. Also, you may not simply have the finances to do so. So you can combine the core and distribution layer into one layer where you're receiving services for high-speed switching, but also implementing your quality of service. And then your core and distribution layer is connecting into the access layer, where again, users and work groups are gaining access to the network. Let's get a little bit more detailed. Cisco wants you to understand the Cisco Enterprise Composite module, and they break the Enterprise Campus down into three separate modules. First, there's the Enterprise Campus, which you've really just learned about. It's the hierarchical model of core, distribution, and access. Then there's the Enterprise Edge, which aggregates the connectivity from the network to remote locations and users and the internet. And then finally, there's the Service Provider Edge, which basically provides a description of connectivity to your providers. Let's dig into this a little bit deeper. Let's draw this out so we can get into this, get into the weeds in this a little bit. So first thing you have is your Enterprise Campus network. So we talked about core, distribution, and access in, for example, a building. Here you see let's say in this situation we have distribution switches, core switches, and obviously we'll have access switches as well, and they're serving, let's say, a server farm for end users. That rarely is this ever built out in an isolated network. So there is a distribution, there is an edge distribution service in this enterprise campus as well. Now this is one module, and Cisco wants you to understand that as one module. Now this edge distribution connects over many times via multiple ways to the edge services, so enterprise edge. And this could be for e-commerce. It could be for corporate internet. It could be for VPN or remote access services or wide area network services. This is the enterprise edge module. And then finally, especially when we're using internet services, there is a third module that you need to understand that we're going to connect into. And obviously, once you make a connection into internet service providers, or for example, your corporate internet is going into a separate internet service provider than maybe your e-commerce sites, VPN and RAS go out to the PSTN, but also connect into internet connections that you may be using. They may utilize internet connections you have running. And then WAN services, which obviously are often run over private circuits, maybe frame relay, MPLS. It depends on how advanced your network is at this point. That being said, this is a third module you must understand, and this is the service provider edge. This is the service provider edge module. So 3 separate modules you need to understand for your CCNP switch exam. The Intelligent Information Network concept is one of the methodologies core to Cisco networking. Now, the concept behind IIN is that a network design should make information available when it's needed by the business processes. One way to look at this is, if I were to ask you to draw out your network, what would you do? What would you start with? Now, many of us would begin drawing out switches and routers and other hardware devices. But actually, when we look at it from the viewpoint of IIN, what we're doing is you're actually drawing it out in accordance with the business process. So instead of drawing the IT infrastructure, what we do is you draw it out in accordance with the business process itself and how the infrastructure would serve that business process. So taking this inclusive design approach by looking at the business process, it will allow you to see which IT components may need to be connected with higher speed links or implemented with additional redundancy. Instead of just looking at hardware and circuits, now we're looking at the business process and how hardware and circuits support that business process. So we're never divorced from the business. We're never in our own ivory tower, I guess you could say. You're always viewing your network through the lens of how it affects the business process you're trying to support. So there's 3 points of integration in IIN, or the points on your network where you can add IIN components. First, there's integrated transport, and this involves the integration of network data, such as voice, data, and video. These components, as you know, make up the Cisco Unified Network, which places these traffic types on any network that is built well, while allowing each to be optimized for usage through traffic management features. Then there is the integrated service component, and this takes common network elements such as storage and servers into account and allows for the function of business services in case of a local network failure. The ability to provide backup or redundant services is due in part to virtualization technology for servers, which allows for these services to be maintained in multiple physical locations at the same time. Finally, the final component is integrated applications, and this allows the network to be aware of the applications that are running over it. When the network is application aware, it can integrate network features to optimize data movement and implement security and provide redundancy. So IIN is a high-level way of looking at your network, but it forces you to ask important questions about your network that you may not normally ask if you're just focused on hardware and circuits. Now that we've talked about IIN, we can talk about Cisco SONA. Cisco Service-Oriented Network Architecture Framework actually applies IIN within the enterprise network. SONA divides the IIN ideal into 3 different layers. There's the network infrastructure layer, interactive services layer, and the application layer. And before we talk about those, let's talk a little bit more about SONA itself. This is an architectural framework that delivers business solutions and unifies network-based services such as mobility and security and the location with virtualization of IT resources. For example, SONA could be used for multi-year projects for the implementation of unified communication systems. You could apply SONA elements to simplify or even enhance the implementation of an IP voice or video or data service on a Cisco network. Let's look at each of the three layers of Cisco SONA in detail. First, there is the application layer or application network services layer. The next layer is the interactive services layer, or what we could say is the interactive services building blocks, and we'll dig into this layer further to explain that concept a little bit more. But finally, there is the network infrastructure layer. Now, the network infrastructure layer is probably the layer that we all understand the most already. And if I asked you to describe the network infrastructure layer, you could probably already do that. The network infrastructure layer is made up of our network devices such as routers and switches, but also other well-known devices such as phones and endpoints such as laptops or even video equipment. So that's the network infrastructure layer. But this network infrastructure layer obviously has to work with the integrated services layer, or these building blocks. So this is the wide area network, the LAN, mobility. These are infrastructure services themselves. And also we think of identity and security services as services of the network, which the infrastructure layer supports. And then finally we have the application layer, such as instant messaging, unified messaging, and video. So you can see we're going from a specific hardware platform and network infrastructure layer up to the integrated services building blocks. So we're talking about higher level concepts. And then finally, we're talking about how all these can be used to support the applications. So the application layer is one distinct layer. The integrated services building blocks, or the integrated services layer, is another unique layer, and then the network infrastructure is another unique layer. This is important to understand these concepts to wrap your head around what Cisco SONA actually is. Three separate layers, critical to proper network design and implementation. So here's what you've learned. You've learned about the LAN hierarchical model. Then we've dug into the specific Cisco models. So we've learned about the Cisco Enterprise Composite model, then Cisco Intelligent Information Network, and then finally Cisco SONA. All these concepts you'll need to understand for the CCNP switch exam. It'll help you in the exam, but it'll also obviously help you in your career. Thank you very much, and good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we will be covering LAN switching fundamentals. So here's how we're going to break it out. We're going to break it out by learning about the different types of switching, then going over some basic fundamentals about LAN switching itself, and finally we will talk about switch table architectures. Now, we often think of switching as performed solely at layer 2, but that's not really the case. Switching can actually be performed at layers 1 through 4 of the OSI model. Now, as you can see, there are many different types of switching based on the OSI model from layer 1 through 4. But then there's also multi-layer switching, which we'll talk about in detail a little bit later in this video. Now, here's some of the basics. Why LAN switches? Why did they overtake the market? There was a time when bridges were quite popular. Well, LAN switches have quite a few advantages over bridges. Specifically, they have more ports than a bridge would ever be capable of supporting. Micro-segmentation allows individual hosts to be connected to individual ports. They operate at hardware speed using ASICs versus software used by bridges. They support layer 3 and layer 4 packet switching by using MLS features. We'll talk about that a little bit later. And finally, probably the most important feature of LAN switching nowadays is the VLANs. So they can use VLANs to create smaller logical broadcast domains on your network. Now, let's just get back to basics here. LAN switching is a form of packet switching, which is used on local area networks. LAN switches provide, and as you already know, they provide much higher port density and at a much lower cost than traditional bridges did. Now there are three main forwarding techniques that can be used by switches: store and forward, cut through, and fragment free. Let's just do a basic drawing here to better understand these concepts. So let me draw out first a frame that is passing through a switch. And then after I draw this frame, I'm going to draw a line here, and that will designate the memory of the switch. So if the frame is passed into memory, we will designate it by going underneath this line. Let's cover cut-through switching first. With cut-through switching, the LAN switch copies into its memory only the destination MAC address, which is located in the first 6 bytes of the frame. The switch looks up the destination MAC address in its switching table and determines the outgoing interface port, and then forwards the frame to its destination through the designated switch port. A cut-through switch reduces delay because the switch begins to forward the frame as soon as it reads the destination MAC address. This is in contrast to store and forward switching. Store and forward switching means that the LAN switch copies each complete frame into its switch memory buffers, and then it computes a CRC check for errors. The CRC check uses a mathematical formula to determine whether the frame is errored. And if an error is found, it's discarded. But if it's error-free, the switch will forward the frame out the appropriate interface port. Finally, there's fragment-free switching, which is also known as runtless switching. Basically, frames that are damaged, which often happen by collisions, are often shorter than the minimum valid Ethernet frame size of 64 bytes. If a frame is smaller than 64 bytes, the switch will discard that frame. Fragment-free is a faster mode than store and forward, but there still exists a risk of forwarding bad frames because you do not have the CRC check. Now, LAN switching can be characterized as either symmetric or asymmetric. Now, symmetric switching provides evenly distributed bandwidth to each port on the switch. And this is typically used in a peer-to-peer desktop environment. Where you see asymmetric switching is when we're talking about endpoints communicating with bandwidth-intensive services such as servers. So this provides unequal bandwidth between ports on a switch. And this is actually the most common type of switching, and it's optimized for client-server environments. You may have a server that demands a 10 gigabit port, where many of your clients obviously don't need that much speed and may only have a 1 gigabit port, or if you have an older switch, a 100 megabit port. Now, in the old days, basic rule of thumb in designing a local area network and wide area network was that 80% of the traffic was going to remain on the local area network. Thus, it was called the 80-20 rule. 80% of the traffic stays local, and you should plan for that. Well, with the advent and with the popularity of the internet and server farms, this has really resulted in the flipping of those numbers. Now we need to design our networks with the idea that probably only 20% of the traffic is going to stay local on the local area network, whereas 80% is going to leave the local area network. So this new paradigm, this new 20-80 rule, places a much greater burden on the network backbone. There are 2 table architectures supported by Catalyst switches, and that's CAM and TCAM. CAM stands for Content Addressable Memory, which is a special type of memory used by Cisco switches. In the case of ordinary RAM, the iOS uses a memory address to get the data stored at this memory location. While with CAM, the iOS does the inverse. It uses the data, and the CAM returns the address where the data is stored. The CAM is considered to be faster than RAM since the CAM searches the entire memory in one operation. CAM tables provide only two results. It's either 0 for true or 1 for false. And it's most useful for building tables that search on exact matches, such as MAC address tables. Now, TCAM, which is ternary content addressable memory, it can match a third state. Instead of just 0 for true or 1 for false, it provides three results, 0, 1, and don't care. TCAM is most useful for building tables for searching on longest matches, such as IP routing tables organized by IP prefixes. The TCAM table stores ACL, QoS, and other information generally associated with upper layer processing. As a result of using TCAM, applying ACLs does not affect the performance of a switch. So TCAM is a very important component of Cisco Layer 3 switches and modern routers, since they can store their routing table in the TCAMs, which allows for very fast lookups, which is considerably better than routing tables stored in ordinary RAM. TCAM is basically a specialized CAM designed for rapid table lookups. Now let's talk about multi-layer switching. Let's understand two concepts first. First, the multi-layer switching engine, which is the MLS SE, which is basically a NetFlow feature card equipped in Catalyst series switches. And then the MLS RP, which is the multi-layer switching route processor, which is a Cisco router with MLS enabled. So understanding those two features will help us understand how multi-layer switching works. Initially, the MLS RP multicasts its MAC addresses and VLAN number to all MLS SEs. Now, because the Catalyst switch has learned the MAC and VLAN information of the MLS RP, the switch can begin the MLS process. So if there's a host A trying to communicate to a host B via layer 3, this packet will be considered the candidate packet. Now the MLS RP routes the packet to host B. Because the MLS SE has learned both this MLS RP and the layer 3 flow in this packet, it completes the MLS entry in the MLS cache. Now it should be noted, after the MLS RP routes this packet to host B, this first routed packet is called the enabler packet. With the MLS entry from host A to host B established, the layer 3 traffic for this flow is now going forward going to be switched directly inside the Catalyst switch without having to go to the router. So multi-layer switching is a play between the routing function of the RP and the switching function of the SE. Once the SE has the information about the flow, it can then simply begin switching this traffic. So here's what you've learned. You've learned about the different types of switching. You've learned some LAN switching fundamentals. And finally, we talked about switch table architectures like CAM and TCAM. So all of these you'll need to know for the CCNP switch exam, and I'm confident you're going to do very well. Thank you very much, and good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we will be going over VLANs. Now, I don't want to assume that you know what VLANs are, so part of it is just an introduction to VLANs. Then we'll talk about VLAN switch port types and VLAN membership for those switch ports, VLAN numbers and ranges, and then we'll talk a little bit about VLAN trunks because it's an appropriate conversation to have, although there is another video that's going to be dedicated solely to VLAN trunking. Then we will talk about VLANs and network addressing, and then finally implementing VLANs on a network. All of these you will need to know to pass your CCNP switch exam. So what exactly is a VLAN? Well, Cisco says it's a group of N stations with a common set of requirements. Using VLANs allows you to put many different devices in many different locations on the same logical network, on the same layer 2 network. In the past, without VLANs, you would have had to rely upon simple hardware solutions, but a VLAN allows you to virtualize your layer 2 segment. VLANs are usually associated by the same subnet, so normally devices on a VLAN are sharing the same subnet. And with this in mind, they're sharing the same broadcast domain. That is the norm. And then VLANs must be routed to communicate with other VLANs. So it is a true layer 2 segment. A VLAN is not going to be able to communicate with another VLAN unless it is passed through a layer 3 device which can route it. Now, there are two types of switch port types for VLAN membership that we need to understand. And the first is the access port. Now, access ports can only belong to a single VLAN. Now, when you think of an access port, it's pretty much probably what you think of. It's usually for end devices like a workstation or a server. It is a device that is an end station, and again, access port can only belong to a single VLAN. Typically used to connect end devices, and there are two methods to assign ports to VLANs. For these access ports. The first, which is by far the most popular, is the static VLAN assignment. So an administrator actually doing it, and then dynamic VLAN assignment, which is done by a server. So let's dig a little bit more into those two concepts. So when we have a static VLAN assignment, the network administrator is actually manually configuring a switch port to be a part of a VLAN. The network administrator is programming the port to say you are going to be an access port and you're going to be associated with this specific VLAN. Now, you can do this dynamically, and this is not as popular, but there is something called a VLAN management policy server, which can assign a desired VLAN to users connecting to a switch. We don't need to get much deeper than that for your exam, but you do need to know these two methods. Now, there's another type of port that we need to understand the concept of VLANs, and that is trunk ports. And trunk ports are used to carry data from multiple VLANs. So access ports only allow communication from one end device over a specific VLAN. Well, ultimately, if you're hosting many VLANs, this traffic's going to need to be able to communicate throughout your network so that they're not limited by a hardware device. So your VLANs may be spread throughout many floors or maybe even many buildings. Trunk ports allow you to carry data from all these different VLANs between all your different hardware devices. Now, there are some standard VLAN numbers and ranges you should know. Specifically, let's focus on 2 to 1001. These VLANs are created and used and deleted on all Cisco Catalyst switches. And another one that you should really focus in on is the range of 1006 to 4094. These are extended. This is an extended range of VLANs for Ethernet VLANs only. Now, you may be asked about these other ranges, but I would focus in on VLAN ranges 2 to 1001 and 1006 to 4094. Now, we talked a little bit about VLAN trunks earlier, but let's just hit upon VLAN trunks a little bit more so we can understand it. Now, again, I want to remind you that there is another video that is dedicated solely to VLAN trunks, but let's just get a basic understanding here. VLAN trunks are used to carry data from multiple VLANs, which you already know. Now, there are two methods, two protocols that can be used to build these trunks. And the first is Inter-Switch Link, or ISL, and that's a Cisco proprietary protocol that is used to preserve the source VLAN identification information for frames that traverse trunk links. And then there is, I would say, the more popular 802.1q, which is an open standard. And then it performs a little bit differently than the Cisco proprietary protocol. Now, the reason 802.1q is so popular is you probably understand that for obvious reasons, that if you want to trunk between two devices, one is Cisco and one is non-Cisco, you're able to do that. So this standard works very effectively, and 802.1q is very popular. But you will definitely be asked about ISL, and you will definitely be asked about the differences between ISL and 802.1q. Now, so you've received a lot of information right now. So let's go ahead and kind of draw out some of these concepts that we've been talking about. So when we think of VLANs, we think first of we need to connect, endpoints need to connect on a local area network. So here we have 4 endpoints, and we have 1 switch. And each of these endpoints need to communicate, and not all of them need to communicate with each other. So let's say we have 2 workstations and 2 servers, and we're going to put this one workstation in VLAN 10 and this other workstation in VLAN 10, and then these 2 servers in VLAN 2. These 2 servers are segmented on their own VLAN, and as are the workstations. They cannot communicate between each other, between VLAN 2 and 10, but anything on VLAN 10 can communicate with VLAN 10. Now here's another dedicated VLAN, we'll say VLAN 3, to a dedicated device. Now, and here is a router. So for any of these VLANs to communicate with one another, they need to pass through a layer 3 device. So this workstation that from VLAN 10, if it wants to communicate over to a server, it needs to be routed and go through the router and passed over to VLAN 2. And let's say you want to keep VLAN 3 devices not accessible from the network. You can prevent that. So here we have other devices on VLAN 3, and we'll say, let's say this is a back-end connection between 2 servers that we have no need to route it. VLAN 3 can be segmented from the entire network. Nobody can reach it. So there's some security built into VLANs as well. Now VLANs can extend obviously over to other hardware platforms. So this router is connected to another switch, and on this switch, let's say that's in a different building, we have another device on VLAN 2, another device, another endpoint on an access port to VLAN 10. And if they want to communicate over to the other building, let's say VLAN 2 or VLAN 10, they simply go over this trunk port, you know that term, goes over the trunk port and can communicate over to the other sites. Configuring a VLAN is rather straightforward. You simply go into configuration mode and type in VLAN. And for the sake of this example, we're assigning it number 10. And then normally you would name the VLAN so anybody logging in would understand what that VLAN, what the purpose of the VLAN actually is. So the purpose of this VLAN is actually to host servers. You can name it obviously anything you want, but in this case we'll just say servers. And then you have the VLAN built, but you still need to assign ports to that VLAN. So you assign a port to a VLAN by actually going into interface configuration mode, and in this example it's fast Ethernet 02. And then you need to make the Ethernet port an access port. Now remember those 2 port types that we're concerned about, access port and trunk port, we're making this an access port, and then you enter in the command switch port access VLAN in the VLAN you want it to participate in. And let's say on fast Ethernet 02 we have a server we're connecting, so we're going to assign it to VLAN 10. And that is it. That is it. So let's tell you what, now that we've talked about how to configure it, let's go ahead and go into the lab and actually configure it. And obviously it's pretty straightforward, but nothing beats actually logging in and just doing it yourself. So, and we can take a look at actually what it looks like when we show some of the information for the VLANs we're configuring. So here we are on a switch. And again, we go into configuration mode, config T. And we simply type VLAN. Now there's many options here, but we're just worried right now about assigning a VLAN to it. So We're going to create VLAN 10, and let's go ahead and name it. And we're going to name this VLAN 10 servers. And let's go ahead and create another VLAN 20, and we'll name that workstations. So let's take a look at what our configuration is. So we simply do show VLAN, and there you will see we have a VLAN 10 and we've created a VLAN 20, servers and workstation. Now notice there's no ports assigned to these. You will see if we scroll up a little bit that by default on this switch, VLAN 1 is already created and the ports are assigned to VLAN 1. Well, we want some of those ports to be assigned to VLAN 10 and 20 because we're going to be connecting some servers and workstations to this switch. So we go into interface configuration mode, and we're going to go into Fast Ethernet 02, and we want Fast Ethernet 02 to participate. We want to make it an access port, so switch port mode access, and then we want to assign it to VLAN 10. Switch port access VLAN 10, and there you have it. Now on port 3, let's assign it to VLAN 20. And obviously we can do more than just one port per VLAN, so let's go ahead and assign port 4 to VLAN 10 and port 5 to VLAN 20. And there you have it. Now if we show our VLAN configuration, you will now see that ports 2 and 4 are assigned to VLAN 10, ports 3 and 5 are assigned to VLAN 20. Fairly straightforward. Now again, they will not communicate between one another, between VLAN 10 and 20, unless they are routed between each other. But that being said, you've created 2 broadcast domains. So here's what you've learned. You've learned about VLAN switch port types and VLAN membership. You've learned about VLAN numbers and ranges, VLAN trunks, VLANs and network addressing, and finally implementing VLANs. You've done it in the lab, and I think you have a really good foundation on moving forward, and good luck in your studies. Thank you very much. Hi, this is David Voss, CCIE 11372, and in this video we are going to be learning about trunking. We're going to go over a basic trunking overview to start, and then we'll talk about trunking protocols, ISL and 802.1q. And then we're going to configure and verify some trunk links, and then we're going to talk a little bit about DISL and DTP, and then finally we will not only talk about but also do this in the lab. We'll be filtering VLANs over the trunk links that we create. The primary purpose of trunking is to carry traffic between switches and to maintain the VLAN information. It's not like an access link though, because a trunk link does not belong to a single VLAN, but instead carries traffic from several VLANs over a point-to-point link. So for example, if you have a port on VLAN 10 in one part of your network, and then let's say on a different floor connected to a different switch, you have another endpoint connected to VLAN 10. VLAN 10 information would be advertised over a trunk link between these two switches so that communications could occur. Now there are 2 key protocols you need to understand for the development of VLAN trunks. First is ISL, which is inter-switch link. It's Cisco proprietary, and what it does is it preserves the source of VLAN information for frames that traverse the trunk links. And then there's 802.1q, which is the IEEE standard. And what this does, it inserts a single 4-byte tag into the original frame. Now, understand that there are many differences between ISL and 802.1q, but just for now, understand that ISL is the Cisco proprietary protocol, 802.1q is the IEEE standard. Let's go ahead and expand upon this concept of trunking. So think of any neighborhood or small neighborhood in a suburb, and there you will see many driveways which generally support just one car at a time. So let's just draw these driveways, each supporting one car. Now, the cars ultimately need to leave the driveway, and they do so by getting on a street where all the cars share the road. So they go from a driveway where it just supports one single car to a street that supports multiple cars, each car trying to get to its destination. And there are certain rules in place so that everything works correctly and everybody goes the right way safely. Well, trunking really works the same way. Think of these as access ports, or driveways as access ports on a switch, where a single VLAN is supported. And think of the major streets as your trunk link, where traffic from multiple different access points or different VLANs traverse the trunk link. So let's draw this concept out further regarding trunk links. You have endpoints or nodes on your network. We'll draw these out, and they each connect to switches. And let's say we have here's a telephone. Endpoints could be a laptop. Endpoints could be a server. They all connect to switches, and they would do so, let's say, via VLAN 10 and VLAN 20. And let's say over here for the phone, he's a participant in a dedicated VLAN 15. They can all access the network through their access ports. But if we need to communicate via the switches, we need these VLANs to pass over these trunk links. So one trunk allows VLAN 10, 20, and 15 to traverse this trunk link. If we add a new VLAN 30, we either could or could not allow it to traverse the trunk link. If there's VLANs in other areas of our enterprise, let's say VLAN 10 and 20 and VLAN 15 are scattered throughout, obviously the trunk links are going to be needed in order for traffic to pass over our network. So as you can see on the trunk links that we're configuring, we configure the VLANs that are allowed over a trunk link that are only needed. So on this example with this switch, we just need 10 and 30 to traverse that trunk link. Between these other two switches, we just need VLANs 10 and 20 and 15 to traverse the other trunk link. Now, ISL operates in a point-to-point environment, and it can support up to 1,000 VLANs. The original frame is encapsulated, and an additional header is added before the frame is carried over the trunk link. And then at the receiving end, that header is then removed and the frame is forwarded to the assigned VLAN. Now there's some other things about ISL that you should know, such as the support for PVST and then the ISL frame information. This is information that will be beneficial for your test. Now, 802.1q, as I said earlier, is much more popular, mainly because it's an open standard. So it inserts a single 4-byte tag into the original frame, and then the trunking device recalculates the frame check sequence before it sends the frame over the trunk link. 802.1q also has a user priority field. Now, if you've worked at all with telephony, this would look familiar to you. The 3-bit field, it refers to the 802.1p priority, and there's 8 separate levels of priority. And then it also has a VLAN identifier field, and this is a 12-bit field that uniquely identifies the VLAN to which the frame belongs. Now, to configure and verify a trunk link, it's actually rather straightforward. To configure it, you simply go to the interface that you would like to create as a trunk link, and you type in the switch port command, and then you type in switch port trunk encapsulation, and you choose which encapsulation you would like to use. So you can use .1q or specify .1q or ISL, or you can have it negotiate. And then finally, you create your trunk, so switch port mode trunk. And that is it. And to verify, you simply type in show interfaces and then the interface that you configured, and then switch port afterwards. Now, Cisco offers dynamic trunking protocols. DISL and DTP help switches automatically negotiate whether to enable a common link as a trunk or not. Now, as the name indicates, DISL supported ISL only. So even though the software was included on all Cisco switches, once 802.1q was offered, Cisco needed to upgrade the protocol. So when 802.1q was introduced, the protocol needed to negotiate whether to use ISL or 802.1q encapsulation. Therefore, Cisco introduced the second generation trunk negotiation protocol, which is DTP. Now, with DTP, if the switch port is in a dynamic desirable state, the port will actively attempt to become a trunk if the neighboring switch is set to desirable or auto. But if the switch port is set to auto, it is passive, and the port will only become a trunk if the neighboring switch is set to dynamic desirable. So let's jump on switch ALS1. Let's configure a trunk between ALS1 and ALS2 over Fast Ethernet 011. So as you remember, we jump on the interface itself, Fast Ethernet 011, switch port mode dynamic to use DTP. Let's set this side to auto, which is a passive state. It's not going to initiate DTP packets. And then on ALS2, let's do the same thing. Let's actually set it to dynamic auto, which people often do, unfortunately. But this side is also now in a passive state. This trunk's not going to come up because both sides of the trunk are passive. You can see, even though we've programmed it correctly, this trunk is not going to come up because this side is set to a passive state of auto. And as you can see on ALS2, you don't see a Fast Ethernet 011 trunk. Even though we've programmed trunking for that interface, it's not showing up. And it's not going to show up until that trunk establishes. So what we need to do on Fast Ethernet 011, at least on one side of this trunk, is change it from auto to desirable. So on ALS2, what we'll do is we'll get back on under Fast Ethernet 011. Let's go ahead and change it from dynamic auto to dynamic desirable so we can initiate some DTP packets and thus bring the trunk link up. And you'll see once we set it to desirable, you'll see this trunk link come up. And there we see Fast Ethernet 011 show up in the trunking table. And it is up and functioning. So here's how you filter VLANs over a trunk. Specifically, use the switch port trunk allowed VLAN command. For example, if you want to specify that VLAN 1, 10, and 20 may traverse the trunk link, you program switch port trunk allowed VLAN 1, 10, 20. If you want to specify that all VLANs may traverse a trunk link except VLANs 10 through 30, for example 10, 11, 12, then you would program switch port trunk allowed VLAN except 10 through 30. And then finally, if you want to specify that VLANs 1, 10, and 20 are no longer allowed to traverse the trunk link, that is, you want to remove them from what you already have programmed, you can do that by typing switch port trunk allowed VLAN remove 1, 10, and 20. These are just 3 examples. There's many options you can use, but these are just 3 examples of how you program filtering of VLANs over a trunk link. Let's go ahead and filter some VLANs over our trunk link. So let's jump on to ALS2. And again, we'll go under Fast Ethernet 011, use that trunk link. Let's take a look at it. You can see that we are allowing all VLANs. Now let's go ahead and begin to filter what VLANs are allowed over this trunk link. So let's go back under Fast Ethernet 011, and let's just allow VLAN 10 and 20 to traverse the trunk link. So we simply type in switch port trunk allowed VLAN 10 and 20, and now you will see the only VLANs that are allowed, the only trunking VLANs allowed are VLANs 10 and 20. Now, let's say we want to remove one of these VLANs. You don't have to reprogram everything. You can simply remove one of the VLANs manually. Let's go back under Fast Ethernet 011. And this time, let's just simply type remove 10. We're just going to remove VLAN 10. Now, VLAN 20 will be the only one showing as allowed over the trunk link, as you can see here. And now let's say we want to add a VLAN over this trunk link without having to reprogram it again from scratch, because oftentimes you can have many VLANs and you don't want to have to redo everything. So we just type in switch port trunk allowed VLAN, and then we type in add the VLANs we want to add. So we'll just say we want to add 30. So now when we check, we will see that the trunk link is allowing VLAN 10, or excuse me, VLAN 20 and VLAN 30. So here's what you've learned in this video. You've received a trunking overview, and you've learned about the differences, the basic differences between ISL and 802.1q. You've learned about how to configure and verify trunk links, and how Cisco's proprietary dynamic trunking protocol can help bring up trunks automatically. And finally, you've learned how to filter VLANs over trunk links. All of this information you're definitely going to need to know to do well on your CCNP switch exam, and I'm confident you will do well. Good luck in your studies, and thank you very much. Hi, this is David Voss, CCIE 11372, and in this video we're going to be talking about the VLAN Trunk Protocol, or VTP. So here's what you're going to learn. We'll be doing a VTP overview, then talk about VTP domains, modes, advertisements, passwords, versions, and pruning. So let's get started. So a quick VTP overview. This is a Cisco proprietary Layer 2 messaging protocol which manages the addition, deletion, and renaming of VLANs on switches in the VTP domain. It allows VLAN information to propagate throughout the switched network. So this is critical if you want to reduce administrative overhead in a switched network. It enables switches to exchange and maintain consistent VLAN information without requiring consistent manual intervention. Now, a VTP domain is basically a group of adjacent connected switches that are part of the same VTP management domain. So note that a switch can only belong to one VTP domain at one time, and it will reject or drop any VTP packets received from switches in any other VTP domains. So if you set a domain on a switch, it will participate in VTP advertisements for that domain. But again, it will reject any VTP advertisements from other domains. Now, here's a real critical concept for you to understand in VTP. And actually, it's very important to make sure your network stays up and running, because often there can be confusion about what these modes, VTP modes, actually do. So not only is this important for your CCNP switch exam, but it's also important for you as you administer your network. The VTP server mode is a default VTP mode for all Cisco Catalyst switches. On a VTP server, you can control VLAN creation, modification, and deletion for the respective VTP domain. What happens is that it stores the VLAN database in RAM, and then it advertises this VTP information to all other switches within the VTP domain. You will see in the lab the effect of programming a server has throughout the VTP domain. Now, each VTP domain must have at least one single VTP server switch. Consider this your administrative switch. Now, the next mode we want to talk about is client mode. In client mode, the switch can advertise and receive VTP information, but it does not allow VLAN creation, modification, or deletion, and it cannot modify or store the VTP database in NVRAM, but it can receive VLAN information, but only from the VTP server switches within the same VTP domain. Now, finally, there's transparent mode, which allows for the creation, modification, and deletion of VLANs, but note this is critical to know about transparent mode. This is only locally significant. So the creation, modification, and deletion of VLANs is only locally significant, and this information is not propagated to other switches in the VTP domain. It passes VTP updates, but it ignores them as far as applying them to the local database. So VTP advertisements are sent out periodically by each switch in the VTP domain via its trunk link. And it should be noted the important configuration revision number. Switches use a configuration revision number to keep track of the most recent information in the VTP domain. This is incremented every time new information is received. The switch with the highest configuration revision number is considered the switch with the most up-to-date information. So this should bring out some red flags for you if you're adding a new switch to the network. If you add a new switch to the network, and let's say this switch has been previously configured or used somewhere else, if it has a more recent configuration revision number and you insert it into your network, the information on that switch will propagate throughout the VTP domain, and all the other switches will revert to that configuration. So you need to make sure when you're adding a new switch to your network, you understand not only what VTP mode it's in, but also what VTP domain it's in, and finally, what configuration revision number it's set at. Well, let's draw this out so we can understand the concept a little bit better. Now this server is going to connect into a client, and let's say we program on this VTP server a VLAN 20. That information is passed over to the client, and the client will learn about that VLAN 20 automatically. Now if that client will then pass that information on to the other switch. Let's say we have another client as well, and that client will also insert VLAN 20 into its VLAN database. Now let's say we have a switch in transparent mode. We will pass VLAN 20 onto this switch. It will not insert it into its local database, but it will pass that information on to the other client for insertion into its database. Now the one in transparent mode, let's say he adds VLAN 17 and 18. Again, these VLANs 17, 18, and 19 are only locally significant, and this information will not be passed on to any other switches. So it can participate in the domain and pass advertisements, but the VLAN you create on a transparent switch will only be locally significant. So if we add VLAN 20, 30, and 40 on the server, and you log on to the client, you will see VLAN 20, 30, and 40 on any client participating in that VTP domain. So let's go ahead and test this out in a lab. So we're going to jump on switch ALS1, and you can see here we have VLAN 10, 20, and 30 on this switch. already programmed, supporting desktop servers and marketing. And now on DLS1, let's take a look, and you'll see that we don't see any of those VLANs. This is because we really don't have VTP up and running at this time. So back on ALS1, we're going to set it to VTP server mode. And we do this by VTP mode and then server. And I believe it already is a server, but now you know how to program VTP mode for server. So ALS1 is going to be our VTP server. ALS2 is going to be a client, so VTP mode client. And now on DLS1, we'll make that a client as well. And on DLS2, we're going to make this a transparent, VTP mode transparent. Now back on ALS1, let's take a look at VTP status just to verify. Yes, here we are. We are a VTP server. But you notice there's no domain name set. Now on ALS2, let's take a look at our status. And we are, in fact, a client. But notice the domain name is already set. So even though he's a client, he will not receive VTP advertisements from the server. Now on DLS1, take a look at status. This is also a client with no domain name set. And finally, DLS2, verifying our status. This is in transparent mode. Now on ALS1, let's go ahead and configure the VTP domain for CCNP. And you'll see here on ALS2, the domain name is mycom. We're going to switch that to CCNP. On DLS1, we're going to switch it to CCNP. And on DLS2, we're going to switch it as well to CCNP. So now they are all participating in the same VTP domain. And now the advertisements will begin to flow between these switches. We show the VTP status. It is a server on ALS1. It is in CCNP domain. On ALS2, the number of VLANs is now matching that of ALS1. Total VLANs 8, whereas before we had 26. So as you can see, it's been overridden, and now our VLAN database matches that of ALS1. On DLS1, we also see the number of existing VLANs is 8, whereas before it was different. And then on DLS2, we can see our existing VLANs is 10. It doesn't match 8. Why? Because it's transparent. It's only going to pass advertisements. It's not going to insert it into the local database. So if we look here on ALS1, again, here are VLANs 10, 20, and 30. Let's just focus on those for now. And DLS1, VLANs 10, 20, and 30. And finally, DLS2, which is transparent, we will not see VLANs 10, 20, and 30. Again, transparent is not going to insert the VLANs into the local VLAN database, although it will pass the advertisement. Now on DLS2, let's change it from transparent to client. And once we do that, you will see the VLAN advertisements for 10, 20, and 30 show up. And there we have it. So there's a basic understanding of VTP in our switched lab. On your CCNP switch exam, you may be asked about the different VTP versions. This is what I think you should know. VTP version 2 offers the following enhancements over VTP version 1. Version 2 offers token ring support, unrecognized type length value support, version-dependent transparent mode, and consistency checks. Version 3 offers the following enhancements over version 2, which is enhanced authentication, support for extended range VLANs, private VLAN support, support for any database in a domain, and it offers VTP primary and secondary servers. Now let's move on to VTP pruning. VTP pruning is rather important because it increases network available bandwidth. And it does so by restricting flooded traffic to trunk links that the traffic must use to reach the destination devices. So in other words, it blocks unneeded flooding of traffic to VLANs on trunk ports that are included in the pruning eligible list. Now this is disabled by default. You need to enable VTP pruning for that to work correctly. Now please note you can only enable VTP pruning on a switch in VTP server mode. You do that simply by going to global configuration and entering VTP pruning. So here's what we've covered. We've gone over VTP, just a general overview, but then we got into the specifics of VTP domains, modes, and advertisements. And then we talked about versions and how version 3 has enhanced the authentication over version 2 so you can use passwords. And finally, we discussed VTP pruning. I'm confident you will need to know all of this to pass your CCNP switch exam, and I'm also confident you're going to do well. Thank you very much, and good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video, you're going to learn about voice and wireless VLAN support on Cisco Catalyst switches. Now, although voice and wireless are not specifically covered on the new switch exam, Cisco does expect you to know how to support your voice and wireless VLANs on the switch infrastructure. So, for example, although you may not be tested on how to set up an IP phone, you can be expected to answer questions regarding how to set up a switch port to support IP telephony. So again, in this video, you're going to learn how to support voice and wireless VLANs on your switches. A Cisco IP phone provides a data connection for a user's personal computer in addition to voice data coming from itself. So this allows one single Ethernet connection to be installed per user and makes maximum use of your ports, even though several different types of data can pass over that port. The voice and user PC ports always function as access mode switch ports, but the port that connects to the switch, that can operate as an 802.1q trunk, or it can operate as an access port. Now, when bringing up a trunk between an IP phone and a switch, this is normally negotiated, but you can specify that the ports at both ends are brought up as an 802.1q trunk. Now, you could bring the switch port up as an access port, but that would not allow you to segment voice and data appropriately. The trunk allows you to segment voice and data on separate VLANs, and this would allow you to easily provide quality of service capabilities to the voice traffic since it's already segmented. To configure the IP phone uplink, you just need to configure the switch port where the phone connects. The switch then instructs the phone to follow the mode that is selected. If an 802.1q trunk is needed, the trunk is automatically negotiated by DTP and CDP. So let's jump into the lab. Now, you can configure the IP phone uplink as a trunk or non-trunk as you remember.
But the real concern, or the real design consideration you need to understand, is how that voice traffic is going to be encapsulated. So the voice packets need to be carried over a voice VLAN. Now your decision is it going to be over a unique voice VLAN or the regular data VLAN? And obviously that's going to affect how you program the switch port. Also, you need to take into account quality of service information. The voice packets will have QoS information that somehow must be carried along. So in order to configure the IP phone uplink, you just need to configure the switch port, the same switch port where the phone connects. And the switch will then tell the phone which mode is selected. Now please remember, if 802.1q trunk is needed, that is dynamically negotiated by DTP, so the switch port does not need any special trunking configuration commands. So here's an example. Now you would use the following interface configuration command to select the voice VLAN mode that you're going to use. So you would type in switch port voice VLAN. Now with this configuration that you see here, we've chosen the VLAN ID. Voice will be tagged as VLAN 100, and then untagged traffic, which is the data, will be assigned to the native VLAN. Now you can see there's other options, .1p, none, and untagged. None is default. So let's go ahead and talk about all four of these options. There are four different types of trunking modes that you can choose from, as you can see here. And the default mode is none, where no trunk is used. All modes except for none use the 802.1q trunk. Now please note, if you do choose .1p, it places voice packets on VLAN 0, which requires a VLAN ID, but it does not require a unique voice VLAN to be created. Untagged mode puts voice packets in the native VLAN, and as you know from native VLAN, it means it does not require a VLAN ID or a unique voice VLAN. Now the typical mode, and probably the most versatile, is the VLAN ID mode. Voice and user data are carried over separate VLANs, and that 802.1q trunk is automatically enabled, again, as you might remember, using CDP, or you can use LLDP, information exchange, between the switch and the IP phone. It would be CDP if it were a Cisco switch, and Cisco phone, or LLDP if it's Cisco and non-Cisco. Now the trunk contains just two VLANs, and that is the voice VLAN and then the data VLAN. Now please note that when an IP phone trunk is active, it does not show up in trunking mode from the Cisco iOS software using the show command. So what you can do, you can verify that the VLANs are actually being carried over the trunk by checking spanning tree. And you will see that spanning tree will have two instances, and again, that'll be one for the voice and one for the data VLAN. And you simply verify that by the show spanning tree interface command. Now, please note, you can verify the switch port mode, whether it's access or trunk, but also the voice VLAN, by typing in show interface switch port command. So take a look at this. You can see here the administrative mode, whether it's dynamic, the operational mode. You can see that it's going to negotiate trunking. It also shows you the access and voice VLAN. So a lot of information is here. And again, this is the show interface switch port command. So we've wrapped up switch port configuration for voice. Now let's move on to wireless. So as you know, Cisco wireless access points provide wireless connectivity for laptops, mobile phones, or anything else that requires wireless access. But these access points connect to access layer switches on the network. and you need to provide segmentation between wired and wireless implementations, and that's normally done through VLANs. So in order to support a particular access point, you should configure the switch in a certain way. And let's say you have 3 wireless LANs that connect to 3 VLANs, 10, 20, and 30. The switch port to the access point would be configured this way. As you can see here, it's set up as a trunk, and we're supporting the 3 VLANs, which each map to the wireless LANs. Rather straightforward. Now, if an access point is operating in lightweight mode, the AP just needs a single VLAN to support connectivity between itself and the wireless LAN controller. This will allow the control and provisioning tunnel to be built and then to transport wireless traffic. And here's an example. Suppose that the lightweight access point is connected to a switch using VLAN 100, and then you have 3 wireless LANs mapped to 3 VLANs, which are, let's say, 10, 20, and 30. The switch port would be configured with the commands as you see here. Remember, in lightweight mode, the access point just needs a single VLAN to support connectivity between itself and the wireless LAN controller. So the VLAN used on the switch port is not related to any wireless LANs at all. The wireless VLANs 10, 20, and 30 terminate on the controller somewhere else in the network. Now, just a reminder, one of the goals of this video was to show you how to set up switch ports to support wireless. Now, you can learn more about wireless implementations on Cisco website, especially if you're not sure about some of the terminology we've used in this last section. So here's what you've learned. You've learned about voice and wireless switch support, specifically how you program VLANs on Catalyst switches. And just a reminder that even though wireless and voice are not necessarily on the switch exam, you may be asked specifically how to set up switch ports to support those technologies. I wish you the best of luck in your studies.
Hi, this is David Voss, CCIE 11372, and in this video we will be covering BPTU. And in this video we're going over some basics of spanning tree. And if we're talking about the basics of spanning tree, you need to talk about bridge protocol data units and also port states. So that's the goal of this video. We'll talk about BPDUs, port states, and then finally we will discuss the importance, or just an understanding, what the bridge ID is and how it's important to spanning tree protocol. STP is defined in the IEEE 802.1d standard, and its primary purpose is to make sure that your network is loop-free. It operates by making the following assumptions: that all links are bidirectional, and that they can in fact send and receive BPDUs, and that the switch itself is able to regularly receive, process, and send BPDUs. Now, all switches that reside in the same STP domain regularly exchange these bridge protocol data units, these messages, with one another. And ultimately, the network uses the information from these data units to determine the network topology and the flows of traffic. The topology of an active switch network is determined by the following 3 variables: the unique MAC address, or the switch identifier associated with each switch, the path cost to the root bridge associated with each port on the switch, and the port identifier. All of these play a big role in the decision making of how traffic will flow on a network. Some basic facts: BPDUs are sent to the STP multicast destination address, as you see here. And by default, they are sent every 2 seconds. Now there are two types of data units that we should know of: configuration BPDUs and TCNs, or topology change notification BPDUs. Now switches determine the best configuration BPDU based on the following criteria, which is lowest root bridge ID, which is based on root bridge ID, root path cost to the root bridge, sender bridge ID, and sender port ID. Before we can continue, we should really understand how things work in spanning tree regarding just the ports themselves. So spanning tree ports. So in a typical environment, we're going to have one root switch, and we have three switches connected here: switch 1, 2, and 3. And switch 1 is the root. And this is going to help us understand how spanning tree designates ports. So in spanning tree, the root never has root ports, because root is always the forwarding port that is closest to the root bridge. So this root only has designated ports. Switch 2 and switch 3 both have root ports. That is the forwarding port that is closest to the root bridge in terms of path cost. And then switch 3 has a designated port. This is one forwarding port on each LAN segment. And then switch 2 is the alternate port. This is the best alternate path to the root bridge on that very same segment. Next to switch 3, we're going to connect switch 4. Switch 3 is going to have a designated port, but it's going to also here have a backup port. A backup port is a backup redundant path to a segment where another bridge port already connects. The backup port applies only when a single switch has two links to the same segment. Now we can better understand the following slide. At the completion of configuration BPDU exchange, the following results. A root switch is elected for the entire spanning tree domain, and a root port is elected on every non-root switch in the spanning tree domain. As you will remember, a root port is a forwarding port that is the closest to the root bridge in terms of path cost. A designated switch is elected for every LAN segment, and a designated port is elected on the designated switch for every segment. And if you will remember, a designated port is a forwarding port for every LAN segment, the chosen forwarding port. And then finally, based on all of this information and all these calculations, loops are avoided in the network. Now, topology change BPDUs play a key role in handling changes in the active topology. They are proactively originated by any switch and sent upstream toward the root bridge, providing information that would be key to keeping the network loop-free. Next, let's talk about spanning tree port states. 802.1d has 5 different port states: disabled, blocking, listening, learning, and forwarding. Let's talk about each of these in depth. When a switch port is in blocking mode, the port is not transmitting or receiving data, and it's prevented from transmitting BPDUs. Packets arriving on the port are not learned by the bridge's filtering database. A block port, though, can receive BPDUs and is included in the spanning tree algorithm calculation. So ultimately, it could be used to transfer data, but it's not. It's blocking at this point. Next, let's talk about the port state of listening. A listening port is not transmitting or receiving data, and packets on the port are not learned by the bridge's filtering database. But it can transmit and receive BPDUs and is included in the spanning tree algorithm calculation. The listening state is a transitional state that will change to the learning state after a settable time of period, which we know as the forward delay timer. Next, let's talk about the learning state. In a learning state, the port is not transmitting or receiving data, but it can receive and transmit BPDUs. It is included in the spanning tree algorithm calculation, and the packets arriving on the port are in fact learned by the bridge's filtering database. This also is a transitional state that will automatically change to a forwarding state after a settable period of time, which is called the forward delay timer. And as appropriate, let's move on to the forwarding state. The forwarding state is the only state in which data is being transmitted and received by the port. It can receive and transmit BPDUs and is included in the spanning tree algorithm calculation. The packets arriving on the port are learned by the bridge's filtering database. Finally, let's talk about the disabled port state. A port is disabled or in a disabled state when the port is not transmitting or receiving data packets or BPDUs and is not considered in the spanning tree algorithm. So as you can see, once a port is enabled by a network administrator or through initialization, it goes through a process or these different port states. The port will move into a listening and learning and ultimately a forwarding state if the spanning tree algorithm has chosen it as a root port or a designated port. If spanning tree has not chosen the port as a root or designated port, it will put the port into a blocking state. You know that also as an alternate port or a backup port. Now, spanning tree uses the bridge ID to uniquely identify each switch, and it's actually used to assist in the election of a spanning tree root bridge, unless, of course, the root bridge has been manually configured. In the 802.1d standard, each VLAN requires a unique bridge ID. So let's take a look at some of these basics with regards to spanning tree. Here we are on a switch. And what we'll do is let's just do a basic show spanning tree. Here you can tell that this switch is in fact the root. There are many ways you can tell which is the root, but the most obvious way is that it says this bridge is the root. The second way you can tell that it's the root bridge is that you notice that the root ID MAC address and the bridge ID MAC address are both the same. Another way you can tell that it is in fact the root bridge is that none of the interfaces for VLAN 1 are set up as a root port. The role is all designated ports, which you will normally find on the root bridge. Now you'll see here on VLAN 20 that VLAN 20 is not in fact root, and I knew that initially not by looking at the root ID or bridge ID, but actually at the interfaces. I can see on Fast Ethernet 07 that it is a root. Now you can see here the status of the interfaces at forward, blocking, forwarding, which obviously you know from what we've gone over already that root ports and designated ports are in forwarding state, alternate ports and backup ports are in a blocking state. Now, let's take a look at a transition of an interface as it goes through the process, through each of these port states. And what we're going to do is we're just going to check on VLAN 1. So let's take a look at Fast Ethernet 07 and watch it transition. Let's go ahead and shut it down. And now you can see Fast Ethernet 07 has gone down, and now you can see that Fast Ethernet is Fast Ethernet 07 is no longer showing up. But watch, because we know that there are set timers with 802.1d, we're going to be able to see it transition as the port comes up and spanning tree calculates. We'll see it transition and going through the certain steps, ultimately getting to its role as a designated port on the root switch. So watch this. And what we'll do here, it's not up yet. There it is. It's listening. And we should be able to see it go through 3 stages here. Now it's learning. And now it's forwarding. So we saw it go from a listening, it went from a disabled state to a listening, learning, and forwarding state. So here's what you've learned. You've learned the basics of Spanning Tree Protocol 802.1d. You've learned the importance of bridge protocol data units. You also better understand port states and the importance as well that bridge ID plays in the entire process of Spanning Tree Protocol. All these things together build for you a really solid foundation as you move forward and learning about Spanning Tree and different variations of it. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're covering Spanning Tree port types, cost and priority, as well as timers. So we'll discuss root bridge election, cost and priority, root and designated ports, and also we'll talk about alternate and backup ports as well. So Spanning Tree root bridge election, following initialization, all switches initially assume that they are root, but the switch with the highest bridge priority is elected the Spanning Tree root bridge. Now, all things being equal, if nothing's been configured and all things are set to default, then the root bridge is chosen by the lowest order MAC address. During root election, no traffic is forwarded over any switch in the same Spanning Tree domain until things are stabilized and there's a loop-free topology. Spanning Tree uses cost and priority values to determine the best path to the root bridge. In the 802.1d specification, it assigns a 16-bit default port cost values to each port. Now, note this before we dig into the actual port values. The port cost is globally significant and is included in all propagated BPDUs. By default, the lower number, the lower costs are more preferred. So you're going to see this in a second as we draw this out. But in the event that multiple ports have the same path cost, then Spanning Tree will consider the port priority. The default value is 128. But you should note that the port priority is locally significant and not included in Spanning Tree Protocol BPDUs. So the Spanning Tree Protocol default port cost, it depends on the interface speed. And you'll notice here from this chart that the higher the speed, the lower the cost. And this comes into play when Spanning Tree is actually trying to calculate the best path to root. So for example, let's draw out a network with 5 switches. And we're going to bring each of these switches online and let Spanning Tree decide which is the best path and which ports should be root, which ports should be designated ports. So they are all interconnected. And let's pretend we are powering them all on. Now, let's say the switches aren't all of the same speed. So, for example, we have a 10 megabit switch, 100 megabit switch, and we'll just say all the interfaces on the switch are that speed. A 1 gigabit switch, a 100 megabit switch here, and a 1 gigabit switch. So as you remember from the chart, these numbers should start to look familiar. The cost of 2 is assigned to a 10 gigabit interface, cost of 4 a 1 gigabit interface, cost of 19 a 100 megabit interface, and a cost of 100 to a 10 megabit interface. And Spanning Tree will calculate, as you can see it's doing right here, Spanning Tree is calculating best path to the root. And let's say we've assigned the 1 gigabit switch as our root. We've manually set it. Spanning tree would then calculate. And as you can see here, from the 10 megabit switch through the 100 meg over to the 1 gig, it's 100, and the total cost is 123. And then the other path, the total cost is 119. That's the lower cost. That would be the root port, because that would be the preferred path. So as you know, we've already talked about some of these ports, but spanning tree elects two types of ports that are used to forward BPDUs, and that's the root port. Now note, the root switch never has any root ports because this is the port that provides the best path to the root bridge. So every other switch is going to have one root port. That's the best path to the root bridge. The root bridge will not have a root port for obvious reasons. The root path cost is calculated based on the cumulative cost to the root. The designated port actually points away from the spanning tree root, and it sits in a blocking state. All ports on the root are designated ports because the root path cost will always be 0. The designated port is the best port on a segment. So for example, on a segment where there is no root switch, you will have one designated port, and all the other ports will be either alternate or backup ports. We talked quite a bit about BPDUs in video lesson 3, module 1, but let's build upon that further. BPDUs include several timers that play an integral role in the operation of the protocol. And the modification of these timers should always be made at the root bridge. There are 3 configurable spanning tree timer values, which is hello, forward delay, and max age. The hello time is the time between each BPDU that is sent, and as you know, it is 2 seconds by default. Forward delay is the time that is spent in the listening and learning state, and you definitely learn about those states, or if you haven't learned it already, go back to lesson 3, module 1 video. But you learned about those states in that video. And the forward delay time is 15 seconds by default. And then max age is set in the BPDU by the root bridge, which is 20 seconds by default. And if you'll remember, the max age timer controls the maximum length of time that passes before a bridge port saves its configuration BPDU information. Although it's 20 seconds by default, you can of course tune this time to be between 6 and 40 seconds. So let's jump into the lab and show spanning tree is obviously going to be one of the most popular commands we're going to run if we want to verify. You can see there's a lot of options here on how to view your spanning tree environment. Let's take a look at spanning tree for VLAN 1. And as you can see here, this bridge is the root. Now, you know from what you've learned so far, how do you know this is the root? There's many indicators. It says it's the root, and there are no root ports. They're all designated ports. Now, as we jump on a different switch, as expected, there is one root port on this switch, and there are 2 alternate ports and 2 designated. So let's take a look at who the root is for each of the VLANs. And you can see that by simply doing show spanning tree root. You can see the root ID. Well, I tell you what, sometimes you simply don't want to wait for spanning tree to tell you who root is going to be. You actually want to set who root is going to be. We want to make this root. And you do this by typing spanning tree VLAN 1 root primary. And as you can see, we've now taken over, DLS1 has now taken over as the root. Usually you like to set in your network who the root is. And you can see here, show spanning tree root. It shows that we are in fact the root. And you can see the default hello, max age, and forward delay timers. Now let's go ahead and reconfigure some of these timers. So we type in spanning tree VLAN 1. Let's change the hello time. We want to send out BPDUs more frequently. Let's change it from the default 2, and we're going to change it from the default 2. And then let's change another timer. We're going to change the max, and then we're going to change max age to 40. Finally, we're going to adapt the forward time to 30 seconds. And now we can show the results of what we've done. So here's what you've learned. You've learned about root bridge election. You've learned about port cost and priority, root and designated ports, and finally spanning tree timers and how to adapt them. Good luck in your continued studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering Rapid Spanning Tree Protocol. We'll do an overview, review BPDUs, look at port states, port roles, and port types, and finally we'll talk about some of the enhancements of Rapid Spanning Tree Protocol over its predecessors. Now, the 802.1d standard was designed at a time when network recovery was not expected to be immediate, and times certainly have changed. And thus, the 802.1w standard, Rapid Spanning Tree Protocol, significantly reduces the time taken for spanning tree protocol to converge when a link failure occurs. Now, network failure to an alternate path can occur in sub-second time frame, so it performs better than traditional spanning tree protocol with no additional configuration. And note, the 802.1w BPDU is similar and backward compatible with the 802.1d. BPDUs are sent every hello time interval, which is 2 seconds by default, and it's the non-root bridges which generate these BPDUs. Topology change notification BPDUs, or TCNs, originated by a switch are relayed up to the root bridge, which then propagates them to all of the other downstream switches. These are some of the most important concepts that you'll need to grasp as you prepare for your CCNP switch exam. Now please note that 802.1d may have had 5 different port states, but 802.1w has 3: discarding, learning, and forwarding. And you can count on the fact that you'll be asked about that in your exam. In 802.1w, there are port roles. There's the root port, defined as the port that receives the best BPDU from the root bridge. It provides the shortest path to the root bridge. And then there's the designated port, which is an active forwarding port that actually points away from the root bridge and toward the edge of the network. It sends the best BPDU on a segment. There's the alternate port, which is the non-forwarding blocking port that backs up a root port. And then there's the backup port, which receives better BPDUs from the same bridge rather than from a different bridge. It's a non-forwarding blocking port, and it backs up a designated port on the same segment. It's much easier to draw these out so we can get a better understanding of what these ports are actually doing and what they actually look like on the network. So here we have our network, And we have 3 switches, all interconnected. And our first switch is our root. We'll call it switch 1, then switch 2, and switch 3. So switch 1 is the root. And again, they're all interconnected. So the designated port on the root is going to be both links. There's no root port on a root because remember, root ports, as you see here on switch 2, are the ports that have the best path back to the root. And switch 3 has a root port and then a designated port. Now remember, a port is designated if it can send the best BPDU on the segment to which it is connected. On a given segment, there can only be one path toward the root bridge, and if there are 2, there's a bridging loop in the network. Therefore, there is one designated port between switch 2 and switch 3. Now you see the alternate port. Alternate port and backup ports have something in common. They are both blocked ports. The alternate port is simply the alternate path for that segment. It's not the designated port for the segment, so it's moved into a blocking or alternate port status. An alternate port receives more useful BPDUs from another bridge, so therefore it is port blocked. Now a backup port receives more useful BPDUs from the same bridge it is on, and it is port blocked. What makes 802.1w perform so well is that the rapid transition feature allows RSTP to place ports in a forwarding state without having to rely on any timer configuration. Now, in order to achieve fast convergence on a port, the protocol relies on 2 new variables. These are edge ports, which are generally connected to endpoint devices, workstations. This immediately goes into a forwarding state by using the port fast feature. Next, there's link type. RSTP supports 2 different link types. Point-to-point, and that's a port that operates in full duplex mode, and shared on a port that operates in half duplex mode. There's some other enhancements you need to be aware of with 802.1w. First, uplink fast. Uplink fast provides fast convergence using uplink groups in the network access layer. So an uplink group is actually, it consists of the root port, which as you know is forwarding, and then a set of block ports. And it provides an alternate path in case the currently forwarding link fails, and it does so immediately. Backbone fast provides faster convergence in the network backbone after a spanning tree topology change occurs. So backbone fast detects indirect link failures, and when the switch receives inferior BPDUs from its designated bridge, and when it does that, it indicates that the designated bridge has lost its connection to the root bridge, and it immediately chooses another path back to root. Let's go ahead and jump into the lab and enable rapid spanning tree protocol and also program uplink fast and backbone fast. So we log into a switch and we type spanning tree mode, and then we choose rapid PVST. And quite simply, that's all you need to enable it. So that's enabled on the switch now. And we are going to go ahead and show. Now you can see that rapid spanning tree protocol is enabled for all of our VLANs. You also see the hello time, max age, and forward delay timers are set to their defaults of 2, 20, and 15. We are going to let's make this switch the root. And we do so by spanning tree VLAN 1 root primary. And we're going to make it the root for VLAN 1 and 10. And by doing so, we allow ourselves to be root for certain VLANs, but not all VLANs. And as you can see here, the bridge is the root. There's some other designations that you can tell that this is root because we're not going to have any root ports. And you will see here we have no root ports as well in VLAN 10. Also, the MAC address for root ID and bridge ID match, so that's another way you can tell that your bridge is in fact root. Let's go ahead and enable uplink fast. And as you can see, it's quite simple. We just type spanning tree uplink fast, and that's enabled on the switch. It's as simple as doing that for backbone fast as well. And to monitor uplink fast and backbone fast, you simply type in show spanning tree uplink fast. And then you can also do show spanning tree backbone fast. So here's what you've learned. You've received an overview of RSTP. You've learned about RSTP BPDUs, port states, port roles, port types, and the enhancements. We also jumped into the lab and programmed RSTP. We enabled it and then enabled uplink fast and backbone fast. And we also took a look at ways you can monitor it as well. This is a great foundation for you for RSTP, and good luck in your future studies. Thank you. Hi, this is David Voss, CCIE 11372, and in this video we're covering multiple spanning tree protocol. So in this video we'll dig down deep into MSTP. We will look into the BPDU format, look at MST regions and region components, internal spanning tree, and multiple instance spanning tree. MSTP is an IEEE standard. It combines the best aspects of PVST Plus and 802.1q. Several VLANs can be mapped to a reduced number of spanning tree instances, since most networks do not need to know more than a few logical topologies. That being said, it's more complex than typical spanning tree protocol, and interaction with legacy bridges will be a challenge. MST uses RSTP for rapid convergence. Therefore, each switch must be capable of processing RSTP BPDUs in order to support MST. Here you can take a look at an MST BPDU format in detail, and you can see the obvious indicators that this surely is an MST BPDU. You need to understand MST regions if you're going to understand MST at all. An MST region defines a boundary within which a single instance of STP operates. MST employs the use of regions because not all switches in the network might run or support MST. Therefore, different kinds of spanning tree protocols divide the network into STP regions. A collection of interconnected switches that have the same MST configuration comprises an MST region. Specifically, the MST region name, configuration revision number, and VLAN to instance mapping. An MST region consists of two separate components: an edge port, which is simply a port that connects to a non-bridging device such as a network host, and then a boundary port, which connects an MST region to a single spanning tree protocol region running RSTP 802.D, 802.1d, or any other MST region with a different MST configuration. So let's talk about MST region components, and the best way to do that is actually to look at this diagram. Here we have MST region 1, 3 switches interconnected. The hosts are connected to edge ports. So remember, there are two types of ports, edge or boundary. the hosts are connecting into edge ports. And the MST region then communicates with other domains or regions using boundary ports. So switch 3 and switch 4 are communicating via boundary ports. Even though they're both running MST, they are running two separate regions and therefore will not share that VLAN information. And then there's 802.1W and 802.1D domains as well. Multiple spanning tree establishes and maintains the following two types of STP instances: internal spanning tree and multiple instance spanning tree protocol. Now, regarding internal spanning tree, the MST region sees the outside world via its internal spanning tree interaction only. The IST presents the entire MST region as a single virtual bridge to the outside world. BPDUs are exchanged at the region boundary only over the native VLAN of trunks, as if a single CST were in operation. IST is the only instance that sends and receives BPDUs. The IST connects all the MST switches within a region. When the IST converges, the root of the IST becomes the IST master. And the IST master election process is similar to that of traditional spanning tree protocol root bridge election. Initially, all switches in a region claim to be IST master, but switches within the region then exchange BPDUs and finally elect an IST master. Now, multiple instance spanning tree protocol represents spanning tree protocol instances that exist only within the region itself. MISTP does not interact directly with the CST outside of the region. Instead, MISTP conveys STP information for each instance within the region. Cisco Catalyst switches support up to 16 MISTPs on a single switch. So let's jump into a lab and configure MST. First thing we're going to do, we're going to set the spanning tree mode to MST, and then we go into MST configuration, and we go into basically revision 1 or instance 1, and we name this region A. So this is our first region, and in this region we are going to allow VLAN 1 and 10. And here, as you can see, you can set priority if you want the switch to become root or non-root as well. This is another popular command for dictating spanning tree and who becomes root in the region. Now, this is the advantage of MST. We can create a second instance supporting VLAN 20 and 30, and we can set a different priority, even though it's on the same switch, a different priority on this switch for whether it should be root or non-root. So the point being, you can have your switch take over root for certain regions, but not all regions when you roll out MST. Now, if you want to show your current MST status, just type show spanning tree MST, and we'll do 1 and 2. Those are our two regions. And you can see here the bridge ID and priority. You can see the status of each of the interfaces and which VLANs are allowed. So here's what you learned. You got a good, solid introduction to MSTP. You saw the BPDU format. You learned about the regions and the components within those regions, the importance of internal spanning tree, and then also learned about multiple instance spanning tree. This provides a really solid foundation for you. You should be able to answer most questions regarding MST at this point. Thank you and good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we will be going over port aggregation protocol. Specifically, you'll get an introduction to it, and then we'll talk about the modes and the learning methods it uses to create an ether channel, and finally we'll go into the lab and we'll do some configurations. So the port aggregation protocol is actually a Cisco proprietary link aggregation protocol, and it enables the automatic creation of ether channels. Packets are sent between ether channel capable ports in order to negotiate the forming of an ether channel, and the traffic is sent to a specific destination multicast MAC address, as you can see. Now, there are specific port aggregation protocol modes that you should be aware of. Now, first, we'll take a look at the on mode, which actually is not a mode of PAGP. What it does is it forces a port to be placed into a channel unconditionally, and the channel will only be created if another switch port is connected and configured in the on mode. That's important to note because there could be some discrepancies, and thus the ether channel would never form. So there's no negotiation when you put it in the on mode. It's simply up and expecting the other side to be up as well. Now, the port aggregation protocol modes are either auto or desirable. Auto is basically a passive mode. It negotiates with another PAGP port only if it receives a packet. Otherwise, it will stay in a passive mode. It will not send any packets. It will never initiate PAGP communications. In desirable mode, this causes the port to initiate negotiation for a channel in another PAGP port. So it actively attempts to bring up the ether channel. So as you can see here, when one switch is configured for auto and the other is for auto, there's no ether channel formed. In any other case, whether it's auto to desirable, desirable to auto, or desirable to desirable, there is an active negotiation request, and therefore the ether channel will form. So let's actually draw this out so we make sure we understand this concept, because sometimes charts don't always do the trick. So let's say we have here two separate switches. And on these switches we have 4 separate ports. And on one switch we've configured it for auto mode and the other for desirable. What happens? A desirable PAGP packet is initiated and the ether channel forms. The next configuration is to have one side as auto and the other side is auto. No initiation packet is sent. They're both passively waiting and no ether channel is formed. Next, we have one side as desirable and the other side is desirable, and initiation packets are sent by both and received by both, and yes, an ether channel will form. Now, finally, if one is sent to auto and the other is programmed as on, there still is no request to initiate. Even though this one is hard up, the on is hard up for ether channel, an ether channel will not form because the auto is still in a passive state and it will never receive a packet from a port that is set to on. So let's take a look at port aggregation protocol in the lab. We are on switch ALS1, and we are going to configure trunking on, or excuse me, we're going to configure ether channel on port 7 and port 8. And you'll see here port 7 and 8 are DLS1. So let's configure an ether channel between ALS1 and DLS1. So first thing to do, let's pick our ports. So we're going to do interface range fast Ethernet 7 through 8. Notice there's a problem here. Although you wouldn't think it's wrong, I did that for a reason. It's fast Ethernet 7, and you need to put the space, so you can drive yourself crazy sometimes, but make sure you have the space in there. And then you assign them to a channel group. We're setting the mode to desirable, so you know what that means. It's going to actively try to establish an ether channel with the neighbor. Now the ether channel is not formed yet, obviously, but you do need to do a no shut to make sure that these ports are up. And now it is actively trying to bring up an ether channel, although that won't happen yet until we program DLS1. So let's program port 7 and 8 on DLS1. Now remember, ALS1 is set to desirable. It's trying to bring up the ether channel. And we're going to set a channel group 1 on this switch, and we're going to set it to auto. Now that should allow the ether channel to come up. And as we will see, there we have it. The port channel is up. And let's do some verification. We're back on ALS1. We can see that we've programmed it correctly. But let's show ether channel status. And there we can see protocol is port aggregation protocol, ports 7 and 8. The ether channel is formed. Now there are different learning methods for port aggregation protocol you should be aware of. Specifically, there's physical learners. These are switches that learn MAC addresses using physical ports within the ether channel instead of via the logical ether channel link. So they forward traffic to addresses based on their physical port via which the address was learned. The switch sends packets to the neighboring switch using the same port in the ether channel from which it learned the source address. This is the default learning method for legacy switches such as the 1900 series. Hopefully you're not bumping into too many of those anymore. Now you really need to be aware of the aggregate logical learners. They learn addresses based on the aggregate or logical ether channel port. The switch transmits packets to the source by using any of the interfaces on the ether channel. And this is the default in current Cisco iOS switches. Now, port aggregation protocol is not able to detect whether a neighboring switch is a physical learner. So when configuring PAGP ether channels on switches that support only physical learning, the learning method must be manually set on the local switch. Then you will set the load distribution method to source-based distribution so that any given source MAC address is always sent on the same physical port. I have a funny feeling you can expect a question on something like this, and it's obviously very important to know. Now, to configure port aggregation protocol, you can see in the lab, it's pretty straightforward. If you're going to set the ether channel to desirable mode, you program channel group, the number, and then mode desirable. If you set it to auto mode, do the same thing, but just select auto. And then to verify your configuration, as you saw in the lab as well, you do show ether channel summary and then show ether channel detail. So it's pretty straightforward. Port aggregation protocol. You got an introduction to it. You learned about the modes, desirable and auto, and then also which modes will work, which modes will not in bringing up an ether channel. Then the learning methods, physical versus logical, and finally the configuration in the lab, and then we did a quick review on how to bring up port aggregation protocol ether channels. You'll definitely need to know this topic, and I'm sure you'll know it well coming forward to your exam. So good luck in your studies, and thank you very much. Hi, this is David Voss, CCIE 11372, and in this video we'll be going over LACP. Initially we'll be just doing an introduction to LACP, and then we'll talk about the different modes, parameters that are set within LACP, and then finally implementing redundancy. We'll also jump into the lab and bring up an Ether channel connection using LACP. It'll be a rather basic exercise, but one that you'll definitely need to know to pass your CCNP switch exam. So the link aggregation control protocol is a part of the IEEE 802.3 AD specification for creating a logical link from multiple physical links. So both ends of the link need to run LACP in order to automate the formation of Ether channel groups. Ports must be the same speed, they must be full duplex, and they must all be configured as either layer 2 or layer 3 ports. LACP supports the automatic creation of port channels by exchanging packets between the ports. It learns the capabilities of port groups dynamically and informs the other ports. All inbound broadcast and multicast packets on one link in a port channel are blocked from returning on any other link of the port channel. Now, LACP packets are sent to the IEEE 802.3 slow protocols multicast group address, as you see here, and they are encoded with the Ether type value as you see listed. Now, there are different types of frames in LACP, and mainly I would just focus on knowing the different components. So there's the collector and the distributor, and there's marker and marker response. So the collector accepts frames from the physical link and passes them to the upper layer. The distributor transmits outgoing frames from the MAC client to links in the aggregation group. And then the marker and marker response are used to maintain frame ordering when moving frames from one link in the group to another. That's about all you really need to know. Now, LACP modes, there are a few of them. See, LACP supports the automatic creation of port channels by exchanging packets between ports. And it does this by learning the capabilities of port groups dynamically. Well, there's two different modes that you need to be aware of. There's the active and passive mode. So these concepts should ring true to you or they should sound familiar to you, because like other Ether channel protocols, one propagates packets in trying to bring up an Ether channel, and another mode sits quietly, passively, just listening. So obviously LACP active mode places a switch port into an active negotiating state in which the switch port initiates these packets, and it actively attempts to establish an Ether channel with another switch that is also running LACP. In passive mode, the port is simply listening, and if it receives another LACP packet, it will then bring up the Ether channel. So it sits and waits. And as you see, depending on what is programmed, an Ether channel will or will not form. If you have two passive ports on either side of the link, an Ether channel is not going to form, because there will be no transmission of packets to try to initiate the Ether channel itself. So let's build upon this concept a little bit further. It always makes sense to draw this portion out to help you understand a little bit better, especially when we throw in the troublesome on setting for Ether channel. So let's say we have two switches. And we're going to have 4 separate ports on each switch. So in the first Ether channel we're trying to develop, we have one passive interface and an active interface, which the active interface is sending the packet, the passive receives it, and yes, they form an Ether channel. The second example, we have two passive interfaces. Neither are sending this initial packet to bring up the ether channel. They will both stay and listen and never form an ether channel. Now, if you have two active ports, they both will transmit LACP packets to bring up the ether channel. And yes, they will bring that ether channel up. And then if you have one port set as a passive port and another hard-coded as on, when it's set to on, it does not transmit anything. It's automatically brought up. So the passive port never receives any packets and the ether channel will not form. So just remember, passive is the tricky part. Passive and passive on are not good combinations to form ether channels. So let's go ahead and jump in the lab. And here we are on ALS 1. And we're going to configure port 7 and 8. So we'll do interface range 7 and 8. And we're going to create an ether channel using LACP, putting them in channel group 1. And let's make the mode as you can see, we have our options here. We're going to choose the LACP mode active. The port channel has been created. Both interfaces are placed within that port channel. And as you can see here, this ether channel is not up yet because we haven't programmed the other side of the link, which is required. So we move on to DLS1 and we program, again, fast Ethernet 7 and 8. We add them to port channel 1. And since the other side is active, just making sure it's not passive on the other side, we're going to program this side to be passive. Now, if this side's passive, that's fine. We'll listen for the proper LACP packets, and this ether channel will eventually come up. And here it is. The ether channel has now formed. So LACP, now this is a very basic configuration of it. You can add IP addressing. There's many different configurations you can do with an LACP, and we'll talk about that in a second. But just understanding how to bring it up, I think right now is the most important thing in the lab. So LACP parameters, there are several LACP parameters that are contained in the PDUs. There is specifically the LACP system priority, and you must configure this priority on each device running LACP. It can be configured automatically or through the command line interface, and it uses the system priority with the device MAC address to form the system ID, as well as during negotiation with other systems. So when I say configure automatically, what I mean by that for any of these parameters is that you could use the default setting or you can manually set it as well. But automatic configuration would be using the default settings. Now there is port priority. LACP uses port priority to decide which ports should be put into standby mode when there is a hardware limitation. LACP automatically configures an administrative key value on each port configured to use LACP. The administrative key defines the ability of a port to aggregate with the other ports. Only ports that have the same administrative key are allowed to be aggregated into the same port channel group. Now, regarding LACP redundancy, see, by default, when LACP is configured on ports, it tries to configure the maximum number of compatible ports in a port channel, up to the maximum allowed, which is typically 8 ports. But if it's unable to aggregate all the ports, then all the ports that cannot be actively included in the channel are then put into a hot standby state. So they could be put to use. They're just maybe not initially put to use. Now, regarding redundancy, LACP one-to-one redundancy is with fast switchover is a popular option because it provides ether channel configuration with one active link and the ability to perform a fast switchover to a hot standby link. To use LACP one-to-one redundancy, configure an LACP ether channel with 2 ports, and you're going to make one active and one standby. And if the active link goes down, then the standby will take over. Now, this must be configured on both ends of the link. And here is how you program LACP one-to-one redundancy with fast switchover. You see here on the port channel, you enable LACP fast switchover, and then you program LACP max bundle 1. And then under interface fast 07, you see that the LACP port priority is set to default. That actually is going to be the standby link, because if you see on Fast Ethernet 08, the port priority is 1 less. And the lower the number, the higher the priority. So Fast Ethernet 08 will be the primary mode of transportation for any traffic going over this channel group. And then Fast Ethernet 07 will be the backup link. So you've gotten an introduction to LACP, and you've learned about LACP modes and parameters as well as redundancy. You have a good foundation of LACP to move forward in your studies, and I'm confident you're going to do well. Thank you very much, and good luck.
Hi, this is David Voss, CCIE 11372, and in this video you will learn about securing switch access, a topic that Cisco wants you to understand for the CCNP switch exam. In this video you will learn the best security practices for Cisco switching. Most of our time will be spent on securing the switch itself, but we will also talk about defending against malicious or unwanted traffic that traverses your switches. You will need to know all of this for your CCNP switch exam. Although some of these topics may seem like simple ones, such as Cisco CDP for example, the fact is you may know about these topics from an implementation point of view, but not a security point of view. Cisco wants you to understand how to protect your switching infrastructure in the new CCNP exam, so you need to look at these topics from a new angle, a security angle. One final note, certain tasks such as setting up passwords and telnet and console access will be covered here, but the specifics of how you do that can be found in the CCNP route courses, so we're not going to duplicate those implementations here. So let's begin. First, the use of system banners. When users access a switch, they need to be aware of specific access or use policies that apply to your organization. So system banners help with that. They display information to the user when they log into the switch. Now, this can be used for users that you would expect, but also for unauthorized users, you can warn them that they are being monitored and that their activities could be ground for prosecution. You implement system banners using the banner MOTD command. This is a typical banner you might see, and basically it's letting internal users know that they must have permission to log in and configure the device, but it's also letting external users know that they are being monitored and that law enforcement will be engaged if any illegal activity occurs. Next, securing the web interface. Now, in most cases, the web interface does not need to be enabled on a switch because in most cases, engineers prefer to use command line. So, in order to disable the web interface, you would do so with the no IP HTTP server global command. Now, if you do decide to use the web interface, then it is suggested that you use HTTPS for secure communications. And HTTPS can be enabled with the IP HTTP Secure Server Global Configuration command. Finally, if you're going to allow HTTPS access, you'll want to limit who can actually access that web page. And you would do that using the IP HTTPS access class configuration command, where you would actually specify an access list that would only permit source IPs from the subnet specified to access the switch web page. Let's go ahead and jump into the lab. Now, if you wanted to disable the HTTP service on the switch, you would simply type in global command no IP HTTP server. And if you wanted to enable HTTPS access, you would type in IP HTTP secure server. Whether you're enabling HTTP or HTTPS, you can limit who has access to that. So if I type in IP HTTP access class, I will reference an ACL, and obviously I need to create that ACL. And in this case, I'm only allowing people on the 10.networks internally to access the HTTP services on this switch. Next is securing the switch console. Now, even though switches are locked away in wiring closets or data centers many times, you always want to make sure that there is a password on the switch console, or that there is authentication of some sort, just in case someone were able to access the switch. Because as you know, once you have console access, you have command and control over the entire switch. The next Cisco recommendation is that you should configure user authentication on all the VTY lines on a switch. You should use access lists in this case as well to limit the source IP addresses, so that it's limited to just the administrative users who would try to telnet or SSH to access a switch. Obviously, SSH is the preferred method. Cisco suggests that you secure unused switch ports by first shutting them down. Anything that's not used should be disabled, and you can do that with the shutdown interface command. You should also configure every user port as an access port with the switch port mode access command. And you should strongly consider using a VLAN that is not in use for those ports, just in case those ports are brought up by mistake and that someone does connect into your network. If they're on an isolated VLAN or an invalid VLAN, they would be able to do no harm. Finally, you should configure the switch port host interface configuration command to force a port to support only a single PC. So as you can see here on the switch, all of the ports are basically either up, but they're not, the ones that are down, they're not administratively shut down. So theoretically, a malicious user could connect a PC to this switch and get an active connection. So what Cisco suggests, and we'll use port 24 as an example, is that you shut down any port not in use. And they also suggest taking the next step with this and assigning it to a VLAN that's not active. So we've created VLAN 999, but on our network, we're not going to be passing traffic for 999. This is going to belong to a port where, let's say on the upstream trunk on this switch, this VLAN never gets passed. And then one final tip they suggest is to type in switch port host if you know for a fact that only a single PC should be connected to this port. And as you can see here, The switch port is set to access, although it already was. Spanning tree port fast is enabled. And then the channel group is disabled. So this is an extra layer of security. Next, you should secure spanning tree. And the best way you can do this is with BPDU guard. Now, as you may know, that a malicious user can inject STP bridge protocol data units, or what we call BPDUs, into switch ports, and this can disrupt your loop-free topology. So if you enable a BPDU guard, that would disable the port immediately when it receives unexpected BPDUs. This is covered extensively in the spanning tree videos. Now, how do you enable BPDU guard? You simply do it like this. Look at the spanning tree options under the interface itself, and you can see here all of our options, but in this case we're going to enable BPDU guard, and it very specifically says it's not going to accept BPDUs on the interface. Therefore, if it does, the interface will no longer pass traffic. That's one way to protect your network. Next, you should secure the use of CDP and LLDP. Now, as you know, CDP lists information, actually quite a bit of information, about directly connected Cisco neighbors. And an attacker can use all that information, such as the device ID, IP address, etc., to assist in an attack on your network. So CDP should only be enabled on switch ports that connect to other trusted Cisco devices. And you disable CDP on a port-by-port basis with the no CDP enable interface configuration command. Now, LLDP is also a neighbor discovery protocol, and this protocol is covered by the IEEE 801.1ab standard. So it allows for interoperability between different vendors. So just like CDP, LLDP uses TLVs inside the messages to encode information about the system. So all this information, such as the system name, system description, the system capabilities, the management IP, port description, etc., are sent between devices, just like CDP. And obviously that's a lot of information that an attacker would love to have. So just understand this, or Cisco wants you to understand this, that you should treat LLDP the same way you do CDP, and that is you limit it only to the ports that you need it to run on. And all of the configuration and show commands in LLDP are almost identical to CDP. Now you can see here with CDP, show CDP neighbor, you can see your connected neighbors and the local interface they're off of. Now this is a little bit of information, but you can get a lot more by doing a show CDP neighbor detail. So this a hacker would love to have this amount of information just on this first switch alone. It tells you the platform, capabilities, what interface it's connected to, it tells you the iOS code, what duplex setting, etc., etc. So it tells you a lot of information about what's on the network, and obviously this is information that should only be shared between trusted devices. Therefore, CDP should only be enabled on interfaces, on trusted interfaces between two Cisco devices that you know need to pass the traffic. If you do not need to pass CDP traffic on your network, then you can disable it and should disable it. So here's what you've learned. You've learned about basic concepts, switching concepts, which I know you've learned before, but you learned about it from a different angle, and that's the security angle. And this is what Cisco wants you to know for the CCNP switch exam. So I wish you the best of luck in your studies. Thank you. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering Cisco port security. Specifically, in this video you will learn about port-based restrictions and port-based authentication. The fact is, networks often must be secured on a very granular level. Cisco wants you to understand how you can leverage your switching infrastructure to protect your network. So to configure port security on an access layer switch port, first you need to enable it on a per interface basis. So let's just go ahead and do it for Fast Ethernet 01. You type in switch port security. And as you will notice here, it needs to be either an access or trunk port or a tunnel port. So let's go ahead and make it an access port. Next, we need to identify the allowed MAC addresses on the port so that we know what can be allowed to actually communicate. Now we can explicitly configure addresses, or they could be learned dynamically. So each interface that uses port security, you can specify the maximum number of MAC addresses that will be allowed to access that port. So we would do that through the following command. Switch port security. Take a look at your options here. And in this case, we would put maximum. And let's say we want to allow a maximum of 5 addresses. So by default, port security only allows 1 MAC address. But obviously we can change that, and we've just done that. We're allowing up to 5. So at this point, it's going to dynamically learn MAC addresses, and then once it learns those MAC addresses, it will expect those addresses in the future. And obviously we've limited it to 5 here, so it will learn up to 5 MAC addresses, and those are the MAC addresses that will be allowed. So being that it learns up to 5 MAC addresses, dynamically, what happens if the switch reboots? It has to then relearn those MAC addresses, and maybe you don't want that. Maybe you want it, once it learns its 5 MAC addresses, you want it to remember those even during a reboot. So you can handle that by doing the following. Switch port security, MAC address, and you can specify sticky. And if you do that, you would then, anything learned dynamically would then be saved during a reboot so that only those MAC addresses would be allowed. Now you've seen in my previous commands when I hit the question mark, you can specify the 48-bit MAC address. So yes, you can configure switch port security MAC address and then put the specific MAC address in. So for example, if you wanted to specify which MAC address is allowed on the port, you could specify by simply typing in the MAC address. And that MAC address would then be allowed, and obviously during a reboot as well, because it'll be in your configuration that you save. Now, what happens if there is a violation? You can choose how you want to handle these violations, and I'll show you that. switch port security violation. And you can see there's 3 options here on how to handle this. So let's talk about each one of these 3. Now, a violation occurs if more than the maximum number of MAC addresses are learned, or if there's an unknown MAC address which attempts to transmit on the port. So at that point, the switch port will take one of the following actions. First, it could potentially go into shutdown. Now, this is where the port immediately is put into an error disabled state, which effectively shuts it down. And it must be re-enabled manually or through the error disabled recovery. Next is restrict. And in this case, the port is allowed to stay up, but all the packets from violating MAC addresses are still dropped. In this case, the switch keeps a running count of the number of violating packets and can also send syslog messages or SNMP traps as alerts of the violation. And then finally there's protect, and this is where the port still stays up, just like the restrict mode, but the packets are still dropped from violating addresses, but in this case there's no record of a violation kept. So now that we're back in the lab, let's say we want to move it to restrict mode. Now what happens when we exceed 5 MAC addresses on the interface? The condition is logged, but the interface stays up because we are in restrict mode. Now, note that if an interface is in the restrict or protect condition, you may need to clear the learned MAC addresses so that a specific host can use the switch port. And you can clear the MAC addresses by simply typing in clear port security. And you can clear obviously all of them, configured, dynamic, or sticky. That's a command you may need to use to clear up a situation where security is prohibiting you from giving access to somebody who really needs it. Now, Catalyst switches can support port-based authentication. And in this case, it's a combination of AAA authentication and port security, and it's based on the 802.1x standard. So when this is enabled, a switch port will not pass traffic until the endpoint or the end user has authenticated with the switch. Obviously, for this to work, both the switch and the end user's PC must support the 802.1x standard. By default, the 802.1x switch port begins in the unauthorized state, so no data is passed. So then either the client or the switch can initiate an 802.1x session. But that authorized state ends when the user logs out. So with 802.1x configuration, we'll just walk through this step by step, but the first thing you would do is you would enable AAA. And then you would define the external radius servers. So you would type in radius server and host. And we'll just say for now 10.10.10.10. Next, you're going to define the authentication method for 802.1x. So in this case, we are going to specify that all radius authentication servers defined on the switch must be used for authentication. So the default group is going to be radius. And now that we have that program, we're going to enable 802.1x on the switch. You do that with the following command. .1x system auth control. And next, you assign the switch ports to participate. So within .1x authentication, so you would go to the interface, and in this case we're in interface fast Ethernet 01. The command is .1x port control, and you see here we have three options: auto, forced authorized, and forced unauthorized. So let's talk about each of these three options. There are three 802.1x states that you should be aware of. Forced authorized. This is where the port is forced to always authorize any connected client. So no authentication is necessary. And this is actually the default state for all switch ports when 802.1x is enabled. Next is forced unauthorized. And this is, in this case, the port is forced to never authorize a connected client, and therefore no traffic is passed. And then finally, auto. Now, in this case, 802.1x performs an exchange between the client and the switch, and then when that authentication has been performed, it moves from the unauthorized to the authorized state. And obviously, 802.1x must be enabled both on the switch and the client PC for that to work. So back in the lab, we'll go ahead and just choose auto. And take a look at Fast Ethernet 01. Not only do we have port security enabled, but we also have .1x authentication. So anything that does connect to this port not only must be have the appropriate MAC address, but there's a dual layer of authentication here with .1x. So here's what you've learned. You've learned about port security and port-based authentication. Both of these topics Cisco will want you to know for the new CCNP switch exam, as it does seem that they are putting an extra focus on security, and these are certainly topics that you will be asked about. So I hope this video was beneficial for you, and I wish you the best of luck in your studies.
Hi, this is David Voss, CCIE 11372, and in this video we're covering multi-layer switching. Specifically, we'll cover inter-VLAN routing, the components of multi-layer switching, demand-based switching and Ceph switching, protecting the route processor, and then fallback bridging. As you probably already know, routing is required to allow inter-VLAN communications. And there's three solutions that may be used to allow and enable inter-VLAN routing on switches. Inter-VLAN routing using physical router interfaces. Inter-VLAN routing uses router sub-interfaces. And then inter-VLAN routing using switched virtual interfaces. Using SVIs is the recommended solution. Let's go ahead and solidify this concept. So here we have two layer 2 switches connecting multiple VLANs, VLANs 5, 10, and 20, and as you can see there's a trunk between the two layer 2 switches. Now for any of these VLANs to communicate with one another, they're going to need a layer 3 device. So these layer 2 devices, these layer 2 switches, connect up to a layer 3 device. In this case we'll say it's a router. Now all traffic that needs to get from one VLAN to another will be forwarded from the switch up to the layer 3 device and back down into the switching infrastructure. So if VLAN 20 wanted to communicate to VLAN 5, it would be forwarded up to the router. If VLAN 10 wanted to communicate to VLAN 20, the same would be true. This would be true for all traffic that traversed from one VLAN to another. If it's from the same VLAN, it would not need to be routed. And although this model does work, multi-layer switching, as you're going to learn, actually allows for much more efficient passing of traffic. And for us to understand the benefits of multi-layer switching, first we need to understand multi-layer switching components. Two concepts, the control plane and data plane, that you need to know. The control plane is responsible for updating and populating the routing table, and the data plane is responsible for the actual forwarding of packets. Supervisor modules are comprised of three integrated core components. The MSFC3, which runs all software processes and supports both the switch processor and the route processor. Next, the PFC3. The PFC makes forwarding decisions in hardware and supports routing, bridging, QoS, IP multicast, as well as ACLs. Finally, the switch fabric. This is the connection between multiple ports or slots within a switch. Next, let's understand this concept of demand-based switching. This is also referred to as flow-based switching. It's a legacy method of implementing multi-layer switching in Catalyst switches. It does require the following components: the multi-layer switching engine, which is responsible for the packet switching and rewrite functions in the ASICs. Now this represents the data plane, as you've heard about before. The multi-layer switch route processor. This informs the switching engine of MLS configuration and runs routing protocols. This represents the control plane. And then finally, the multi-layer switching protocol. This is a multicast protocol used by the RP to communicate with the SE. The Supervisor 720 supports Ceph architecture for forwarding packets. Ceph operates at the data plane and is a topology-driven proprietary switching mechanism. It uses two data structures for switching: the forwarding information base and the adjacency table. It uses the fib to make IP destination prefix-based switching decisions. The adjacency table is created to contain all connected next hops. An adjacent node is a node that is considered one hop away. That is, it's directly connected. Catalyst switches allow for the optimization of Ceph using two methods: accelerated Ceph, which only allows a portion of the fib to be distributed to capable line cards, and then distributed Ceph, which refers to the use of multiple Ceph tables distributed across all line cards. The fib table of the SP must be exactly the same as the fib table on the RP. On the RP, a ternary content addressable memory TCAM stores all IP addresses in the fib. Each entry consists of these fields: a prefix, this is the destination IP address or IP subnet that is concerned; the next hop that is associated with this prefix. The possible next hop values are receive. This is the prefix that is associated with MSFC interfaces. This entry contains a prefix with a mask of 32, and that corresponds to the IP address of the layer 3 interfaces. Attached, the prefix that is associated with the connected network. You could also see the IP address of the next hop. And finally, in the final category is drop, whereas all packets that match an entry with drop are in fact dropped. And then there's the interface column. That is the outgoing interface for that destination IP address or IP subnet. Let's get back to talking about the route processor. Now please note the MSFC can be oversubscribed because the PFC can forward up to 30 million packets per second, whereas the MSFC is typically capable of forwarding only up to 500,000 packets per second. This can lead to problems such as routing protocols getting out of sync, or even the console on the switch getting locked up. MLS rate limiters limit the packets per second rate of certain packets that are punted to the MSFC. The 6500 series support Ceph rate limiters and also hardware rate limiters as well. Now please note that MLS does not work for all routed protocols. Non-IP protocols such as IPX and AppleTalk are forwarded using software. So fallback bridging is used to bridge non-routable protocols. It creates a spanning tree instance for each bridge group and is configured on a physical layer 3 or SVI interfaces only. But it is a solution that can be used to bridge non-routable protocols. So here's what you've learned. You've learned about inter VLAN routing. You've learned about key MLS components, demand-based and Ceph switching, how the RP is actually protected, and then finally fallback bridging. This provides a solid foundation for learning more about multi-layer switching as you prepare for the CCNP switch exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering high availability introduction and the Cisco supported protocols to ensure a highly available environment. Now, this term high availability is considered a very broad and general term. Let's get more specific as to how it applies to the devices that we'll be supporting. Availability is calculated mathematically and is often expressed in percentages. Surely you have seen some of these calculations in your place of work. Percentages are often calculated from failure rates and repair times. So different types of high availability include service level high availability, system level high availability, and network level high availability. Let's first understand what reliability and serviceability are, because these help us understand the calculations that are used to understand if we have a highly available environment. Reliability measures the ability of a system or a solution to function without interruptions. And the most common measurement you've probably seen regarding this is mean time before failure. Serviceability refers to the time it takes to restore a system to service following a failure. A commonly used metric that you've probably seen for this is mean time to repair. Let's start talking about some of the specific protocols that Cisco supports on the devices to provide highly available environments. HSRP is a Cisco proprietary first hop redundancy protocol. Two versions of HSRP are supported on iOS software. Version 1, and this is the default HSRP version. And this restricts the number of configurable HSRP groups to 255. I don't expect you should be exceeding that anytime soon. And then there's version 2. Some updates to version 2. It uses a new multicast address, among many other things that you can see here. Finally, HSRP authentication gives you the option of plain text or MD5 authentication. MD5 authentication can be configured with or without keychains. When implementing HSRP, two or more routers are configured with a standby IP address on a broadcast interface, usually an Ethernet segment. So while they will each have a local IP address, in this case .2 and .3, a passive election is held to determine the active router, which is actually answering for the gateway IP address .1. The active router answers ARP requests for the standby IP address with a virtual MAC address, so that the host sends packets to the gateway IP address, winds up sending it to the active router. Now, if the active router dies, then another election is held. And in this case, traffic would go out the .3 interface, even though traffic would still be pointing to the virtual .1 IP address. So let's configure HSRP in a lab. First, we're going to assign an IP address to the interface. Then we're going to assign the virtual IP address. This is the IP address that will answer as the gateway between the devices that are running HSRP. Then you can manually set the version number, so we'll run HSRP version 2. And then the timers, so the hello interval, this is how often a packet will be sent to notify the other routers or devices participating in HSRP that this device is active. And then after 30 seconds, it would be declared down. And we can set priority if we'd like, and the higher the priority number, the more likely it will take over as the active router in HSRP. If we set it to 1, it's really going to be the gateway of last resort, only after the other devices have failed. And then finally, you can set up authentication for HSRP to make sure that communications are secure between the devices while it's running. VRRP is an open standard first hop redundancy protocol which elects a virtual router master and then virtual router backups. You can configure up to 255 virtual routers on an interface. That is, if your system is capable of handling it. The default VRRP priority value is 100, and that's important to note because the lower you set it, the less likely it's going to take over as the master. The higher you set it, the more likely it will be. The virtual router master is in charge of sending advertisements to the other routers in the same group. And VRRP, it should be noted, can support both plain text and MD5 authentication. So let's say we have 3 switches with VRRP, which is non-proprietary. In VRRP, one router is elected as the virtual router master, and the other routers are acting as backups in case the virtual router master fails. So in this case, the master has been elected. Dot 3 and dot 4 will serve as backups to dot 2. Dot 2 will answer to the virtual IP address, and if it were to fail, then a backup device would take over. In this example, that would be the dot 3 device. And if the dot 3 system failed, then the final backup system, dot 4, would take over. So let's configure VRRP in a lab. First, we'll set an IP address on the interface. And then next, we'll set the virtual IP address. Next, we'll configure the advertise timers. So this configures the interval between successive advertisements by the virtual router master in a VRRP group. The unit of interval is in seconds. The default interval is 1 second, and all routers in the VRR group must use the same timer values. Then we set the priority. The default priority is 100, but we're going to knock that down a bit so that this device does not take over unless absolutely necessary. And then finally, you can configure authentication. Next, let's cover GLBP. GLBP allows multiple gateways in the same GLBP group to actively forward traffic. So instead of just one device forwarding traffic, you can have multiple. Gateways communicate via hellos messages that are sent by default every 3 seconds. The GLBP group members elect one gateway to be the AVG. Now the AVG answers all ARP requests to the virtual router address and assigns a virtual MAC address to each member of the GLBP group. GLBP has many other features, but you should really focus on the fact that GLBP does provide load sharing and many different load sharing methods, host dependent, round robin, and weighted. And it does support plain text and or MD5 authentication. But the big advantage, and the question you're most likely to get regarding GLBP, is when would you use it? And you would use it if you would like to load balance between devices. GLBP provides a standby IP just as HSRP, but it also provides multiple virtual MAC addresses. So when a host on the connected network sends an ARP request, one of the routers answers with the virtual MAC address. Now this does allow for load balancing. You can load balance across multiple systems instead of just relying on one system to serve all the traffic. In this case, we're going to load balance 50% to router 1, 20% to router 2, and 30% of the traffic to router 3. This can be done because you're using virtual MAC addresses, which take turns answering traffic requests. If a router were to fail, the other remaining routers could take over for all the traffic. Here's an example of GLBP programming. As you can see, an IP address is assigned to the interface, and then a virtual IP address, 10.0.1.1. The timers, hello timer, is set to 10 seconds, and after 30 seconds, this device would be considered down and no longer participating. Then also note that the load balancing configuration as well, which is weighted. Now remember, there's many different types of GLBP load balancing. The key to remember is that that is one of the advantages of GLBP. Should you be asked on the CCNP switch exam, load balancing is a key feature of this protocol. And then finally, as you can see, you can set up authentication. IRDP allows hosts to locate routers that can be used as a gateway to reach IP-based devices on other networks. When the device running IRDP operates as a router, router discovery packets are generated. When the device running IRDP operates as a host, router discovery packets are received. IRDP uses ICMP router advertisements and ICMP router solicitation messages to work effectively, and it eliminates the need for manual configuration of gateway addresses on the network. In this specific example, we have 3 routers, router 1, router 2, and they're given certain priority levels of 190. And we have a third router brought online, which queries the network. It receives responses from the other IRDP routers, notifying the new router that they are available to route traffic. They are put in the local table for that router, and the router then forwards the traffic to the appropriate gateway. Should router 1 fail, then traffic would be forwarded over to router 2. All of this is done without manual configuration for gateway IP addresses. So here's what you've learned. You've received a basic introduction to high availability, and then you've also learned about the specific protocols that Cisco supports in order to ensure a highly available environment. This is a solid foundation for you as you prepare to pass your CCNP switch exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be going over hardware high availability. In previous videos we've talked about different high availability solutions that Cisco offers, but specifically we're going to talk about Cisco hardware and how the Cisco hardware can provide high availability. You're going to learn about supervisor redundancy, route processor redundancy, stateful switchover, stack-wise technology, and power redundancy. So we're going to be talking about a lot of concepts, and it's time to put our thinking caps on. Not a lot of configuration, but more just concepts. Before we dig into hardware high availability, let's first get some terms straight so we understand what we're talking about as we move forward. Terms like failover, hot standby, primary, and secondary. So failover is a situation where a platform experiences a problem that make it impossible for it to provide its normal functionality, and therefore a second device immediately takes over for the failed device. Hot standby is when we have two platforms that are deployed in a failover topology. When the second platform is in standby and it receives from the active platform all subscriber state updates and keep alive messages. So the standby platform is ready to take over immediately. The terms primary and secondary refer to the default status of a particular platform. The primary platform is active by default, while the secondary device is the default standby. Note that these defaults apply only when both devices are started together. If the primary platform fails and then recovers, it will not revert to active status, but remains in standby status while the secondary device remains active. It's important to understand failover and hot standby and primary-secondary concepts prior to moving into talking about hardware high availability. The first topic we're going to cover is supervisor redundancy. Some Catalyst switches support redundant supervisor modules. The first supervisor that boots up is referred to as the primary or active supervisor engine, and the second supervisor is referred to as the standby or redundant supervisor engine. Now, a failover or switchover to the standby or redundant supervisor engine happens when the primary supervisor engine fails or crashes, when it's rebooted, when an administrator actually forces a failover, or if the supervisor obviously is physically removed, there's going to be a failover. The standby supervisor engine is only partially booted and initialized, so not all switch subsystems on the redundant supervisor become operational. The standby supervisor only becomes operational when the following occurs. All switching modules are reloaded and powered up again. Remaining subsystems on the MSFC are brought up, and ACLs are reprogrammed into the supervisor engine hardware. Now, this is important because the failover or switchover process generally takes between 2 to 4 minutes. Now, there's something called Route Processor Redundancy Plus, and this improves on failover, and failover generally occurs within 30 to 60 seconds. The redundant supervisor is fully initialized and configured. Although initialized, the redundant supervisor is still not fully operational, but it synchronizes user-entered CLI commands incrementally, line by line. Now, when a failure or failover occurs, when a failover or switchover occurs with RPR+, the following events occur on the switch. Initially, traffic is disrupted until the redundant supervisor engine completes the takeover. The switch maintains any static routes across the switchover, but the switch does not maintain any dynamic routing protocol information. It clears the fib tables and the cam tables, and then state information, such as active TCP connections, are not maintained during switchover. Now, stateful switchover is actually the preferred redundancy mode for supervisor engines. The supervisor or standby supervisor engine is fully booted and initialized. Configuration information and data structures are synchronized, and it maintains state information between the redundant supervisor engines. Failover or switchover generally happens within 0 to 3 seconds, and administrators can initiate a manual failover to the standby supervisor engine almost seamlessly. Now, the next topic is Cisco Stackwise technology. Specifically, the Cisco Catalyst 3750 series switches support this technology. This allows up to 9 switches to be combined into a single logical unit. The switch stack is managed and configured from a master switch. The stack master is elected upon initialization based on the following criteria, as you see here. Now, there could be stack master, there could be an election held, but it's only held when one of the following events occurs. When the whole switch stack is reset or rebooted, when the stack master is reset, powered off, or removed from the stack, or when switches are added to the existing stack. Now, Cisco Stackwise technology supports multiple high availability mechanisms. Now, regarding power redundancy, there's 2 power redundancy modes which are supported. There's combined and redundant. In combined, both switch power supplies are used at the same time by the switch. The total power load cannot exceed the sum of both supplies. And this is typically used when the switch has a large number of power over Ethernet modules. In redundant mode, the switch draws power from both power supplies, and the switch uses no more power than the capacity of a single supply. So here's what you've learned. You've learned quite a bit about redundancy. You've learned about supervisor redundancy, route processor redundancy, stateful switchover, stackwise technology, and power redundancy. All of these are hardware solutions to make sure that networks stay highly available. You'll need to know all of this for your CCNP switch exam, and it sets a really good foundation for you. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're covering SNMP and IPSLA. Specifically, we're going to learn about SNMP and we're going to go into a lab and configure it. We're also going to learn quite a bit about IPSLA and syslog as well. So all of these can help us maintain a highly available network. Let's begin with SNMP. SNMP is an application layer protocol that provides a message format for communication between SNMP managers and agents. SNMP provides a standardized framework and a common language used for the monitoring and management of devices in a network. The SNMP framework has three parts: an SNMP manager, an SNMP agent, and a MIB. Let's cover these in depth. The SNMP manager is the system used to control and monitor the activities of network hosts using SNMP. The most common managing system is called the Network Management System, or NMS. The term NMS can be applied to either a dedicated device used for network management or the applications used on such a device. The SNMP agent is a software component within the managed device that maintains the data for the device and reports these data as needed to managing systems. The agent and the MIB reside on the routing device or the switch. The SNMP agent contains MIB variables whose values the SNMP manager can request or change through get or set operations. A manager can get a value from an agent or store a value onto that agent. A key feature of SNMP is the ability to generate notifications from the SNMP agent. These notifications do not require that the request be sent from the SNMP manager. There's unsolicited messages or notifications, and these can be generated as traps or inform requests. Traps are messages alerting the SNMP manager to a condition on the network, and inform requests are traps that include a request for confirmation of receipt from the SNMP manager. Now, notifications can indicate improper user authentication or restarts, the closing of a connection or loss of connection to a neighbor router, or other significant events. Traps are often preferred because informs consume more resources in the router or on the switch in the network. Unlike a trap, which is discarded as soon as it is sent, an inform request must be held in memory until a response is received or the request times out. Also, traps are sent only once, while an inform may be retried several times. The retries do increase traffic and contribute to higher overhead on the network. There are three SNMP versions that you should be aware of. Version 1, which is the full internet standard defined in the initial RFC 1157. SNMP version 2C, which is community string-based administrative framework. The C stands for community, and it is an experimental internet protocol defined in RFC 1901, 05, and 06. Now, that being said, SNMP version 3 is an interoperable standards-based protocol defined in RFCs 2273 and 2275. SNMP version 3 provides secure access to devices by a combination of authenticating and encrypting packets over the network. The security features provided in SNMP version 3 are as follows: message integrity, which ensures that a packet has not been tampered with in transit; authentication, which determines that the message is actually from a valid source; and encryption, which scrambles the contents of a packet to prevent it from being learned from an unauthorized source. Let's go into the lab and configure SNMP. The first thing we'll do is we'll define an SNMP community string. We use an SNMP community string to define the relationship between the SNMP manager and the agent. The community string acts like a password to regulate access to the agent on the router. So we configure an SNMP community string by simply typing SNMP server, community, and then the string we desire. Now, if we want our switch to send traps, we need to define that in SNMP as well. We do that through the SNMP server host command. We simply type in SNMP server, the host, and the host ID, which is normally the IP address of the host, and then what we would like to send to the host. Also, you can specify what version of SNMP you are running and if you are running authentication as well. A popular use of SNMP programming is when someone sets the contact location and serial number of the SNMP agent so that these descriptions can be accessed through the configuration file, and so that should somebody want to pull up information about the device, they can easily do so via SNMP. To configure contact location and, for example, and serial number, you simply type in SNMP server and then contact, and you would put the contact name or the phone number, SNMP server location, and then where it actually is located, and finally SNMP server chassis ID, which is where you would enter the serial number. Now, to monitor SNMP status, which we'll do now, let's check all of the changes we've made. We can do that very simply by typing show SNMP. On to IPSLA. IPSLA allows you to monitor, analyze, and verify IP service levels. It's comprised of two components, a source and a target. Operations can broadly be categorized into 5 functional areas. Let's take a look at an example. You can use IPSLAs to monitor the performance between any area in the network, core distribution, and edge, without deploying a physical probe. It uses generated traffic to measure network performance between two networking devices. So as we draw this out, this shows how IPSLAs begins when the source device sends a generated packet to the destination device. After the destination device receives the packet, depending on the type of IPSLA's operation, it responds with the timestamp information for the source to make the calculation on performance metrics. It then can communicate with a performance management application via SNMP to provide real-time analysis of the network. It should be noted that IPSLA can communicate with any IP device on the network that's enabled for these types of measurements. You're probably already aware of syslog, that it's a protocol that simply allows a host to send out event notification messages. A syslog daemon or server is an entity that listens to the syslog messages. It uses UDP as the underlying transport mechanism. There are additional high availability tools that can be used on the network. These include Cisco iOS Embedded Event Manager, which provides real-time network event detection as well as onboard automation, and Cisco Network Analysis Module, which improves network performance visibility to help manage application delivery. Let's take a look at Cisco Works LAN management solution. This is an excellent tool to ensure that you have a highly available network. There are many different modules that can be used or applications, such as Cisco Works Health and Utilization Monitor, Device Fault Manager, to name a few. Cisco Works LAN management solution is an integrated suite of management functions that simplifies the configuration, administration, monitoring, and troubleshooting of Cisco networks. Now, there are many functional areas that you should know about, but specifically, let's talk about monitoring and troubleshooting. You can quickly and proactively identify and fix network problems before they impact end users or services. So here's what you've learned. You've learned the basics of SNMP and a good foundation for moving forward in your studies. You've learned about IP SLA and how basically it works on the network. You've received a refresher in syslog. And finally, we briefly covered some additional high availability tools. All of these will provide you a solid foundation moving forward in your studies.
Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering logical switching, a topic that will definitely be on your CCNP switch exam. So in this video you're going to learn about Cisco logical switching. You're going to get an overview of it, and then how you can create a highly redundant and flexible network by leveraging this technology. And then specifically, we're going to talk about some of the technologies that help support these types of environments, such as Cisco StackWise and Cisco VSS, or Virtual Switching System. So let's begin, and let's talk about leveraging logical switches on the network. Consider the network you have before you. You see two switches in the access layer, two switches in the distribution layer, and two switches in the core layer. They're labeled A1, A2, D1, D2, and C1, C2 accordingly. Now, in a typical network, it's going to be built out with redundancy and high availability. So as you're aware, spanning tree protocol will place some of the redundant links in blocking mode, which prevents bridging loop structures from forming. The end result is a highly redundant network, but the problem is it doesn't really use the full capability of all the ports available and all the bandwidth available. Now, arranging the switches in pairs does provide switch redundancy, but only in the distribution and core layers. The access layer switches cannot provide redundancy. So users who send their traffic, they are not going to be spread across two access switches. They're going to be connected to one switch, and if that switch fails, they will be isolated from the network until somebody actually physically moves them to a different switch. And with these independent access switches, that also causes some design issues, because no direct link exists between two access switches, as you will see here, and typically they never do. Therefore, each access switch would support a different VLAN for the end users. And if you have many users fed out of one access layer, let's say room, you're very likely to have several switches and several different VLANs to maintain, which is an administrative burden. So one possibility to make the situation better and to have a more efficient design would be able to make two redundant physical switches into one logical switch. So a single logical switch can then use the redundant links to their full capability by bundling them into an ether channel. And therefore spanning tree protocol is not needed, and you can use the full capability of the uplink bandwidth. Now, the pairs of redundant links to the distribution switches are configured with ether channels, and now you have no blocked links, and now all links can actively send and receive traffic, and that obviously improves or increases the available bandwidth. Also, as referring to what was pointed out earlier, if you have one logical access switch, it allows for one VLAN to be used to support all of the users. And then you would only have to configure and manage one logical access switch rather than these two physical switches. So the logical switch supports one control plane for management, but it has two separate data planes that are found in, obviously, physical switches. Now let's relate this concept to ether channels. So an access switch, logical access switch that is, still has two uplinks, one to each of the distribution switches, and that's organized as an ether channel. But it's possible now for one of the two ether channels to be blocked by spanning tree protocol, so that only one ether channel is used to pass traffic. So again, all links might not be used. So to continue the improvement of the design, you would use a logical switch in the distribution layer. So now, as you can see, the network design, instead of all of these separate physical switches, it is now, as you can see, two logical switches in the access and distribution layers. A1 and A2 are combined, D1 and D2 are combined, and they're connected by a single ether channel. And all the links can be used now at the same time, so bandwidth is maximized. And let's say a link does fail. The ether channel is not torn down, and it will continue to work with the remaining ports that are available. And now that there is a single link between the switches, spanning tree will always remain unblocked. And ultimately, this topology, even though spanning tree protocol works very well, this topology is much more stable because the ether channel, this stays active even if there is a lower layer issue, the lower layer than layer 3. So let's say there is a spanning tree protocol issue. The ether channel will still stay active and traffic will still pass. So as you can see here, going with logical switching or a logical switch architecture can greatly simplify the whole network, but more importantly, increase performance. So you have your redundancy, but now you also have ease of administration and increased performance. So it makes a very big impact on the network. Now, in order to support this logical type of switching, one technology that you would use would be Cisco Stackwise. So in the past, access layer switches were, really used as independent physical devices. And then if you did have multiple switches in one location at the access layer, which was typical, you had to then configure links between them, and you had to be concerned about configuring each of them uniquely, and there was a lot of administrative overhead and a lot of planning. But Cisco introduced Stackwise technology and Stackwise Plus technologies. And what this does, it enables these separate physical switches to act as one single logical switch. So now you can see we're circling back on what we talked about earlier, but now you're seeing specifically how Cisco makes physical switches logical ones. Cisco Stackwise is available on many switch models, but particularly you may be tested on the fact that they are available on the Cisco Catalyst 3750, E and X series, as well as the 3850 platforms. Now, to create a stacked switch or a logical switch, the individual switches or the individual physical switches need to be connected to each other using a special purpose cable. It's not your typical cable, it's specifically for this technology. And each switch will support up to 2 ports or 2 stack ports. And the switches are then connected in a daisy chain fashion, one switch connecting to the next. And then There's one final connection at the very end, making sure that we have a closed loop. So, in essence, in creating this one large switch, you're just extending the switching fabric. You can stack up to 9 physical switches in closed ring fashion. One of the big advantages of this technology is that you can add or remove switches without breaking the path between the switches completely. Therefore, maintenances become a lot easier, or dealing with failures becomes a lot easier, because the ring can be broken and you can add or remove a switch, but the remaining switches stay connected because of the rest of the ring that is still in place. So there is only one switch that can be considered the stack master, and that is the switch on which you would perform your management functions. With the master switch concept, even if that master switch were to fail, another member switch could take over the role. Finally, let's talk about virtual switching system, or Cisco VSS. Cisco obviously has a lot of switches that are chassis based with slots, and these slots can contain many different types of switching modules. The chassis, they must contain basically the brains of the operation, or a supervisor module that handles all the switch management functions for the switch itself. But Cisco wants you to know about VSS. So with platforms such as the Cisco 6500 or 8500, what you can do, you can configure 2 identical switches to work as one logical switch. And this is called VSS, or Virtual Switching System. And when they are working together, they're considered a VSS pair. But the key to remember is one supervisor of one of the chassis controls the whole operation, or the entire operation of the logical switch. So if it were to fail, the supervisor in another chassis would take over. And to build this logical switch, again, these 2 chassis must be linked together, but they must be linked together by multiple interfaces, and you must configure these interfaces as a virtual switch link. It appears from the study material that Cisco is not so concerned about how you configure these logical switches or the logical switching technology. But that being said, they do want you to understand how it works. They do want you to understand the benefits of it, and they do want you to understand how you would roll it out from a design perspective. So again, here's what you've learned. You've learned about logical switching, and then specifically how to support logical switching with very specific technologies that Cisco gives you, such as Cisco's StackWise, and then finally the VSS, or Virtual Switching System. This is the level of detail that Cisco expects you to know. They are not expecting you to understand how to configure these things, it appears, from the study materials. So I think you'll find that what you learn on your video is going to be very close to what you'll need to know for the exam. And again, you can double check that by looking at your study materials. But we've covered these topics, I believe, to the level of detail that Cisco is going to expect you to know it. Good luck in your studies.